Hello and welcome to Func Prog Sweden 11, last one of this year. And today, as it's the last one, we will have almost like a bonanza. 4 presentations, so welcome everyone. I'll head straight over to the agenda for tonight. First, short introduction by me. Then, how Griffin uses TAP and Portal to understand and debug their event-driven architecture by James. Then a sweet beginner's guide to Scala by Daniel. And then we head over to reduce system complexity with data-oriented programming by Yehonathan. And last but not least, this is not a monad tutorial by John. But before we begin, I would like to thank Azariah for the kindness of the video sponsorship this year. Azariah is an IT consultancy company based in Stockholm with office in Ho Chi Minh in Vietnam also. If you want to know more about Azariah, check them out on azariah.com or in social media. Also, I want to push a bit for the coming schedule next year. Second week of January, we'll run a meetup from Vietnam, because I will be in Vietnam. Then 17th of January, we're back here in Stockholm and running another meetup. And then we'll have meetups in February, March, and onwards. If you want to support the community, of course you want to support the community, you should join the meetup community over at MeetUp, the Func Prog Sweden community, of course. You should follow our channel on YouTube. And if you really like functional programming, you should get a t-shirt like I'm wearing, and you can get it at funcprogsweden.myspreadshop.net. It's the perfect gift for your partner for Christmas, we all know. Try it out. If you have any questions during the presentation, please use the YouTube chat, and I'll read it up for the presenters. With that said, let's start. First presentation. Welcome, James. And I'll do a short introduction of you, James, and I'll hand you the cable.
Thank you.
So, let's see if James, a technology leader with 2 decades of experience, building digital products and high-performing teams. He started his career as a software developer, but had an early interest for people, process, and psychology, pulled him towards leadership. Welcome, James.
Thank you so much, Magnus.
You're very welcome. So you've actually been a software developer, and now you're going to present.
That's right.
I'm just joking with you, sorry. Sorry. Yes, your presentation. Welcome, James.
Thank you. And thank you for inviting me back. It's an honor to be back here.
Yeah, you're very appreciated.
Hi, everyone. Today I'm going to be talking about how Griffin taps into one of Clojure's superpowers. So first, I'll introduce myself. My name is James. I'm the VP of Engineering at Griffin. I've been doing that job for almost 2 years now. And my background is in technology leadership. I've been doing that for a while before I was a software developer originally. Pretty much my only claim to fame in the Clojure community is that I led the team that invented and published and open sourced a software architecture called Polylith, which is starting to take off a little bit in the Clojure world. So if you haven't checked that out, do take a look at that. Okay, what are we going to be talking about today? So the 2 things in orange are the important, cool ideas, concepts that I want to teach you a bit about or show you. But to get to those, we need to go through some context. So the sort of final destination, the exciting thing, is how we do debugging in this event-driven system that we have using TAP and Portal. So if you're into Clojure, you might have heard of or used those before, so we can show you a little bit about how that looks like in an event-driven world. But to understand that, you really need to understand a bit about the platform and the sandbox that we've built. And then to understand the platform, you really need to understand the architecture that we're building that platform on top of. And the cool thing that I want to show you and talk to you about there is transducers. And that's a more sort of general functional programming concept. So even if you're not in the Clojure world, understanding that might be cool. So for Clojure people, there's something, and just for people that are interested in functional programming, there's hopefully something. And to understand about the architecture, we need to understand a tiny bit about the business. I promise I'll try and whiz through the non tech stuff and get to the good stuff as quickly as possible. But I think it is important to understand each step along the way. So let's dive in. Griffin, the business, what are we doing? So we're building a banking as a service platform for fintechs to build their financial products on top of. So what that looks like right now, if you're a fintech, is you have to understand this immense financial ecosystem. You either have to choose to build your own parts of these jigsaw pieces, or you have to integrate with existing platforms that tend to have been around for a while. They're not always well documented. Their APIs can be of varying levels of quality, is perhaps a polite way of describing it. So that makes it much slower, much more costly to get to market. You know, if you've got this brilliant idea that you want to test, having to arrange all those jigsaw pieces and figure it out, that's not easy. So our whole strategy is to make that much, much smoother, much, much faster by building a platform that takes away the pain, the complexity of all of that. So that means that if you're a brand, a big brand like Apple, and you want to do embedded finance, or you're a much smaller fintech and you're starting up and you're trying an idea, both of them could come and use our platform and build their idea as quickly as possible, with one of the unique selling points being we're also becoming a bank. So we're applying for a banking license in the UK, which means that if you're a fintech and you need money, we can also lend you the money or help you out with other financial services. So it's sort of a win-win situation. Okay, so from a sort of high level, what does that look like in terms of what's the USP or how we do things differently? So we're the orange box in the middle, so that's Griffin. And what we're doing is we're building on top of an existing financial ecosystem, that's the gray boxes underneath, and then we're offering that service via API first to our customers. So those are the blue boxes, the different types of customers that we work with. So it's all about wrapping that complexity that exists in the financial ecosystem that I was talking about, offering these clear products via a nice API that's well documented, that makes it really easy and fast for our customers to launch their products and get off into the market. Okay, so now that's the business. Let's dive into the architecture. So how have we built this? You'll maybe notice first the Clojure logos everywhere. It's a 100% Clojure shop, so it's Clojure script in the UI, Clojure on the back end, Clojure in the API. So it's Clojure everywhere. That's cool. But let's go through from top to, I guess, the middle to start with. So you've got the customer, they're making requests to our API. As you do to the endpoints, the API is checking, do you have the authorization and the authentication, i.e., are you allowed to make that request? If so, passes it through to the main system proper. And we're using Foundation DB as our event source queue. So what that means is each request gets placed in the queue, and then we have the brains of our architecture we call procs. I'll explain what those are later, but basically you can think of it as the brains. That's where the business logic lives, and each proc is a little process that is listening on the queue for a particular message that it understands. And when it finds a message like that, it says, I know how to process that. So it takes it off the queue, does some processing, and then puts messages back on the queue for other procs to listen to carry on the processing. So essentially, the procs are talking to each other, but they don't know about each other. They're talking via the messages. So that gives you a really nice decoupled architecture that scales really nicely. And they also use FDB for local storage. And then on the other side, when we're connecting with these third parties, so when we're connecting with that financial ecosystem I was talking about, it's basically the mirror opposite. So we're still using FDB for queuing outgoing requests, and then we have a service gateway, which you can think of as a wrapper that essentially hides away the complexity of their APIs from the system and gives you a clean boundary, if you like, a gateway. And then on the way back in, once we get the responses back from the gateway, they get queued up and they come in as though they're requests from the API. So it's basically a perfect mirroring. And then worth mentioning, we have a UI as well as the API. We think that most of our customers will build against the API because they're building their own applications, web, mobile, or whatever. But the UI is there, so we can sort of be the canary in the coal mine and test the API, make sure it makes sense and you can build UI against it. But also for smaller companies that maybe want to get up to speed faster with onboarding their customers or managing their cases using our ready-made UI. So that's the basic architecture. Let me take a quick sip. So I'm a very visual person, and I like metaphors. They help me to think about things. So if you're not a visual person, you can just ignore this and think about the previous diagram. But for those of you that like metaphors, so what am I showing here? So we imagine our system as a body, and imagine that the way it interacts with the world is through the senses, like listening or sight. So that's the API to our customers and service gateway to the third-party services that we talk to. So that's how we're getting messages in. And then we have a nervous system which transports those messages up to the brain where we're doing the main processing. So think of the procs as the brain, Foundation DB as the transport system or your nervous system, and then your senses are the input and output to that. So when I showed this, a similar slide to the last one, about a year ago when I was talking about banking on Clojure, it wasn't Foundation DB. The rest of it looked very similar, but we were using Kafka. So what we essentially did last month was we ripped out the spinal cord and the nervous system of our platform, and we put in a new one, and we did it without the procs noticing that anything had really changed. So that's a difficult engineering problem, and it's obviously big props to our fantastic engineers. But one of the secrets as to how we were able to do that so smoothly is because procs are transducers, and this is the first cool functional programming idea that I wanted to share with you. So what does it mean that procs are transducers? Maybe I'm just explaining one word that you don't know with another word that you don't know, and that's not too useful. So I will try and quickly explain transducers. To be honest, Rich Hickey has done really good explanations of this, and it's taken him like an hour each time, and he's much better at explaining things than I am, so there's a risk you're not going to fully understand them after this, but hopefully you'll get a little bit of an idea. So transducers, they're a certain type of function, and they're functions where you can describe a transition using a step. So you can go from one state, give a recipe or a set of instructions for how you get to the next state. So if you can't describe the function in that way, it won't be a transducer. What's special about transducers is they're agnostic to both the input and the output states, if you like. They're essentially just describing the step in the middle, and they don't care where they get the input from, and they don't care where the output goes to, which turns out to be very useful. We'll come back to that one. And at sort of a high level, you can describe them as composable transformations. You're transforming one thing into another thing in a step-by-step process. Okay, let's dive into some examples because it's always difficult to understand things just in the abstract. So this is some pretty basic Clojure code where we've got a high-level function filter. It takes a function odd that is true or false, and you pass in a collection, in this case a vector of 5 numbers, and that outputs the filtered collection. So if you've seen Clojure before or any other Lisp, hopefully this looks pretty familiar. So what about this is a transducer? Well, nothing yet, but if we change the arity, and instead of passing in both the collection and the function to filter, and we just pass in the function, then what Clojure is building is a transducer. So it's a recipe for what you do. In this case, you're filtering odd numbers out of whatever gets passed in. So why is that interesting? It's because what happens if instead of passing in a sequence like we've done here, that we pass in a channel or a queue or something where you're just getting one number at a time, because we're describing as a recipe or a set of instructions what you do on each step, we've taken away that connection, the tangling up that happens when you're taking both the recipe and the ingredients, if you like, and you're actually using them to bake the cake. I apologize for my metaphors, but so what we're saying is let's not bake the whole cake, let's just keep the recipe separate. Like, recipes are so powerful because I can share them with people, and it doesn't matter where you get your tomatoes from or exactly what your oven looks like, right? The important thing is that you know what to do. Hopefully that makes sense. Okay, here's another example, map inc. That's also a transducer, but in this case, that's mapping increment across whatever you pass in. Again, it can be a channel, it can be a collection, or whatever. And then I said before that they compose really nicely together. So you can use the comp function in Clojure and just place them together. And what that will do is build a combined instruction or a combined recipe that first filters and then maps increment. And like I said, Rich Hickey has explained how these work, and he actually goes into the underlying implementation details, which I've kept this at a much higher level. So if this sounds interesting, and I think it really is interesting, take a look at these two YouTube videos, well worth your time. Okay, so why do we use transducers in our architecture? Why are procs transducers? First and foremost, it makes them composable. It gives us this really nice abstraction where we can say, given this set of inputs, here's how I do that processing, and here's an output. And that's a really nice way to build things. And because they can compose together so nicely, as you saw on the previous slide, it means we can combine them in a multitude of ways, which turns out to be a great building block for your architecture. Another powerful thing is they're agnostic. What I mean by that is they're agnostic to the input and the output, which makes them incredibly flexible and really good for testing. Because in production, originally we had Kafka, so obviously that's this advanced queuing system that's sending you each message one at a time. But when we were testing, we could just say, here's a sequence of messages that's just a vector. And the transducers, they don't care where that's coming from. And what that meant was they didn't care whether it was coming from Kafka or whether it's coming from, as it does now, Foundation DB. It's just completely, they're agnostic to that. So that's incredibly powerful. And then last but not least, they're fast, they're performant, and that's because the way they're implemented, it's eager, not lazy, and that they don't build intermediate state as they're going. So even if you've got a composed version that has, let's say, 5 steps, they will run that on one version of the data that they're passing over. And when you're building a bank, you want it to be fast. So, okay, let's look at an example proc then. So this is one for making a deposit. It has an ID, so this is a map enclosure, and the ID is basically its name, so it's make deposit proc, and it has a map of messages. So it takes certain messages in, it says, I know how to deal with that kind of message, and when I do, I'm going to output this message or set of messages. In this case, each one only outputs one message, but it could output several. So it's like I take in this message, I output this message. And what's good about this is it's very data-oriented. I know there's going to be a talk later about data-oriented, but obviously it's very declarative. It's not code, it's just data, and that makes it really easy to reason about. So when you're looking at this code, you can understand really quickly, okay, here's what's going to come in, here's what's going to come out. And the constructor is, that's X form is what you call, or XF is what you call a transducer. So let's zoom in on that one. So let's not look at flat map, or let's just, what's happening here is we're taking a message, so that's the unit that we're passing over. That's the unit that we care about, and we don't care where that message has come from, like I said. And all we're saying is we're going to look at the message type in the message, and if it's one of these ones that we know how to deal with, we're going to dispatch to the business logic that deals with that code. And it keeps it nice and simple, it makes it very powerful, and like I said before, makes testing a breeze. Cool. So we're whizzing through this. Let me exit that one and show you the sandbox. So this is our website, griffin.sh, and one of the cool things that you can do now, since we launched it just a couple of weeks ago, is use our sandbox. So what that is something where, as a developer, you can just sign up and give your name, your email, and create an account, and then you're off and in our sandbox, and you can start writing code against the API or using our UI, which is what I'm going to show you later. So why would that be interesting to do? Well, perhaps you're working on a side project and you want a more realistic API to try your code against. Maybe you're fed up of just doing some Twitter API or some, I've seen one where there's like a beer collection from, I think it's Brewdog, where you can sort of see all the beer bottles and create a web app or whatever. But with this, you can actually play around with a real production API. We have good documentation for getting started with it, how you set up your API keys, the HTTP headers, etc., how you can onboard customers, how you can do standard banking things like create bank accounts, make a payment, etc., etc. So that feels kind of cool that we have that possibility that you can use that, but what does it actually look like when you're in? So this is what the sandbox UI looks like. And there are two main sections, one for managing your customers and one for managing banking, payments, and bank accounts. So let me just show you quickly, because here's one I prepared earlier. So this is running on my local machine, so I can show you the debugging, which we're going to get to hopefully quite soon. But normally this will be, you'll be connecting to our platform, obviously, that's running on griffin.sh. Okay, so we've onboarded a customer. What that means in banking talk is that we are doing checks on that customer to make sure that they're not going to commit fraud. Because don't forget, our customers are fintechs or bigger companies that are wanting to offer financial products. So they need to make sure that the companies that they're, or the customers or individuals that they're doing business with aren't going to cause any problems for money laundering or fraud. So we run automatic checks that make sure that that all works well. And then once you've onboarded a customer and they've got an account, you can do fund transfers and send money between accounts. Okay, enough talk about the system. Let's dive into some actual code. So let's hop over to Visual Studio Code and let me explain what you're looking at here. Maybe I zoom in a little bit. Okay, yeah, that should be big enough. Okay, so what I want to show you is this window on the right here, which is called Portal. So Portal it's a tool for improving your debugging. And how it does that, let me show you instead of talking. So to fire that up, you require the Portal API as Portal, you define and you open, and in this case I'm in Visual Studio Code, so I've opened the version that actually launches within the editor. And then all we need to do is to connect Portal to Clojure via this add tap, which is a built-in command in Clojure. So that adds, this function will be called with anything sent via tap chevron. So what this is doing is connecting Portal to Clojure, and then if we go to some code here, okay, so this is deep in the proc part of our code base, and here's an example transducer. You remember I said if it's called xform or xf, that means it's a transducer. So that we won't look at exactly how this is working, but the important thing here is we've done the comp, just like I showed you before. So this is a transducer, this is a transducer. Each step here is a transducer, and what it returns is a combined transducer. And one step is about tapping out some messages. So what we're going to do is we're going to go in here and do some live coding and hope this works. We're going to tap out hello world. And let's execute this in the REPL. Nice, and then fingers crossed, if everything's worked well with my local dev setup, it should appear here once we've done a refresh of a page. Let's have a look if that works. It's always exciting with live demos. Now, it doesn't seem to be working, so that's interesting. Let's see if we can figure out why that is. That one and that one again into the REPL. Might need to restart. I should have tested this just before I came live, of course. Interesting. This is always what happens when you do live demos. So let's close Portal and let's see if we can get it running again. Okay, so that seems to be working now, hopefully. Move that across to the right. I'm not sure why it lost connection there, but yeah, 251 hello worlds. Let's clear that and let's just double check, is that working now? Fingers crossed, otherwise the rest of the demo will be very short. Yes, great. Nice, we're back in business. That was exciting. Okay, so back to where we were in the code. So why is it useful to use tap and Portal? That's what I want you to understand here. Why wouldn't I just do a print line or a log? And the reason is when you do print line or log, what's happening is you're sending strings, essentially, to a file normally. And strings can be useful, and if you pretty print them, it's great. But in Clojure, we have the power of A, a REPL, and B, that we have these data literals. Data-oriented, coming back to that. So what that means is if we get rid of hello world, and instead we send the message that's being passed through. Let's execute that, send it to the REPL. Let's clear that one. Let's go back and refresh. Fingers crossed. Yes, great. So these are all the messages that the system has created to render that page. And what's happening is, as we're scrolling down, what we're doing is we're going backwards in time. The way that Portal works is it appends from the bottom, if you like. So the very bottom message here is the very first message that's sent to start rendering that screen. So this first message, let's look at the message type. It's a session authenticated message. So it's about security and checking that we have the rights to access that page, right? So, but here's the cool thing. Because this is data, what this is showing us is we have, let me go all the way back to the top, there are a lot of messages here. So we have 51 messages, and those are in a sequence. You can see the normal brackets. These more curly brackets show us that we've got a map. So we've got a sequence of maps. And then we can see this map has 7 key value pairs. This one has 16. And because Portal understands that this is data and not just strings, it can have context-aware ways of viewing this data. So we can switch it from the inspector view to a tree view. So that enables us to go much deeper into the code. So if there's nested data structures, this is going to automatically open all of those up and let us go very deep into the data. That's cool. What else can we do? If we go back to the inspector, I selected the wrong thing here. Yeah, top level. So that's the other cool thing. You can choose to change the view just for specific parts. So at the top level, I've said inspect view, but let's say I just wanted to make this one look like, say, a table. I can do that, but you'll see the rest still have the old inspector view, which is nice. And you can do other things. It knows that this is an instance or a timestamp. So here we can say, show me that as a date time, or show me that as relative time, which I find really useful. So we know that that happened 2 minutes ago. When you're debugging, having that ability to see that rather than a timestamp that you need to constantly be thinking, well, when was that? That can be really powerful and really useful. And when you have nested, you can just hit space and expand down into your nested data structures and just explore them that way if you don't want to view them as a tree. So it just gives you this really powerful way of moving around the data that you're exploring as you're working with the REPL. You can also do filtering. So what was the name of that? It was something like session authenticated, was that? So if we do a filter that says session, let me zoom out a bit now. Oh, okay, I see what's happened. So what happens is, where you're selected, that's where it does the filtering. So I thought I was filtering on the main list, but actually I think I was just filtering there. So if I now go to the main list and start typing, let's see if that works any better. Yeah, you see now it's selecting and filtering. So again, when you have lots of messages like we do, if there's only one particular type of message that you're interested in, being able to quickly filter down to that feels like a bit of a superpower. Okay, so we've looked at messages. Let's go back and see what else we can figure out about this by also looking at, let's say, so we've got the message, and let's add the proc as well. So proc, and then we're using both of the arguments that are being passed in, and let's see what that looks like when we evaluate it. Clear out this old one, and head back over to here and refresh. Okay, page is refreshed. Okay, so all those messages that bounce around the system, and let's switch this view. Let's switch the top one down to a tree. So then we're seeing both the messages and the proc. So the proc tells us which is the processing unit or the processor that's dealing with that message, and then the message, of course, has all the detail about the message itself. So again, super useful. And is there anything we can, if we switch back to the, Sorry, I'm trying to do coding remotely from a screen that's quite a long way away, so it's a little bit tricky to see. But let's expand one of these. What's interesting to pull out of this is probably the message type. Yeah, let's pull the message type. So if we copy that one, so as well as pulling the message out to the top level, what we're going to do is pull out, if I can type message dash type, and then we'll grab that one out of the message. Nice. And was there something similar that we could grab out of the proc? What's useful here? Probably the ID, which is essentially the name of the proc. And that way, if we pull these out to the top level in our map here, it's going to help us to know. So we'll call that proc ID, paste that, grab that from the proc. Let's execute that. Clear our portal again. Go back and do a refresh. Okay, and now what we'll do is we'll switch this to a table view. And the reason it knows that we can do a table view there is because what Portal is doing is detecting that it's a sequence of maps, and it knows that if it's a sequence of maps, then I can easily turn that into a table where each row is each entry in the sequence, as it were. So now we've got message type, we've got proc, and we've got proc ID. Nice. So imagine if you're working on this system, just being able to quickly whiz around, see the different messages, see a message that you're not expecting to turn up in a particular order. It's really powerful. And we've only just sort of started scratching the surface with Portal, because it has some features where you can write your own views. So these are the default views in Portal, but you can actually write your own and do some really clever things with visualization and showing nodes and edges in a graph. And one of the things I'm excited by is we make quite a lot of use of finite state machines in some of our procs for managing state and transitioning between different states. And I'm sort of imagining what would that look like if we could visualize each state and the different transitions in a really nice way. When you're debugging the code, suddenly you've got this new way of looking and thinking about what you're seeing in a way that just working with a REPL or just working with logs doesn't quite give you that same level of power. I just want to show one other cool feature. You can select, let's find two messages that are similar. You can actually select multiple entries and do a diff. Let's select this one and this one. So I've command selected, and you have all these commands built into Portal, including a load of core functions. So you can do sort of basic programming here, but what we're going to do is do a diff between those two. These two were so different that maybe the diff isn't that useful. But sometimes you're going to be getting bits of data back that are similar, but you can't quite see where is that different. I was expecting those to be the same, and you just grab them both, you do the diff command, and then it immediately jumps out, it's different here. And again, it speeds you up. It's about being faster with your debugging. It's about getting to see your data in a clearer way, and it's about getting things solved quicker. Cool, I think that was it in terms of the demo. Was there anything? I can't think there was anything else I wanted to show. Let's hop back to the presentation. Okay, we did the sandbox demo, did the tap on Portal demo, which we got working. Okay, what have we learned? So, even if you haven't fully understood transducers, hopefully you've understood something about how flexible and powerful they are, and a little bit about why we chose to make them such a core part of our architecture. And again, it's the fact that they ignore, or not ignore, they don't care about, they're just the recipe, they're just that part, and they don't care about the ingredients or which oven, right? Remember that metaphor? Which makes them incredibly powerful. And then tap and Portal. We didn't talk much about tap. Let me just say what tap is. So tap is this built-in function that's been in Clojure, I think, since 1.10. And the basic idea is to output data rather than just text, so that you can create different visual ways of working with it, such as Portal. And there's been some other things like Rebel and some other tools that you can use that really enable you to sort of dash around your data in a much more powerful way than just with a REPL and or outputting text. And that was it. Thank you very much.
Thank you very much, James. I will run on stage. Thank you very much, James.
Pleasure to be here again. Thank you.
Yes, you're welcome.
Shall I just unplug?
No, leave it in. Leave it in. No, please stay.
Oh, please stay.
I have some tough questions for you.
Oh,
or
fire away.
Joking. No, first, brave that you did live coding.
Yeah, it almost totally failed.
Yeah, and then it doesn't work. What do I do? The stress is just immense. Slides, will they be shared afterwards?
Can do.
Yeah?
Yeah.
Great. Also, I want to push a bit for your presentation the last time you were here. You did banking as a service. You can see it in the channel if you just check around in the Func Prog Sweden YouTube channel. We will also I saw that you had some links to the
transducer talk.
They
They were more just strings to search for, but maybe we could post the links.
We'll post the links in below the vid so people can see them if they want to. Also, I got one question. One question. Why did you shift from Kafka?
I thought somebody might ask that.
Yeah, I would. If no one asked, I would.
Yeah, it's a long story, but the short way of answering it is basically non-functional requirements.
Oh.
So the way that we architected the system is a lot of procs with a lot of messages, which means that you're sending these messages all the time, and it basically wasn't fast enough. So we're not saying Kafka's slow. It was just the way we were using it meant too many network hops. Exactly. And what we didn't want to do was to I was talking about these procs being a great building block. What we didn't want to do is sacrifice that and start saying, well, let's just make bigger and bigger procs that do more and more and become more and more monolithic. That isn't a good way out. So we looked into different options, and it was our CTO, Alan, that discovered that FoundationDB had a lot of the same sort of scaling and reliability properties, which you need as a bank, obviously, but it gave us a lot when it came to performance, and it also is better around transactions. So it's actually ACID compliant as a database, and what that means is we can do a number of these message hops within a single transaction. So it's basically within memory, so it's not going over the network, and then you transact the entire thing. So in terms of performance, it's night and day with what we have with Kafka.
Yes. And now you're not just, Griffin is not just bank as a service, it's actually also a bank. Does it mean that anyone can come to you and just say that I want to use it? Or I guess there are some vetting done, or?
There's definitely, so the onboarding that I showed.
I'm just very curious myself.
The onboarding that I showed,
yes,
that was from a customer perspective. So that's our customers onboarding their customers. So we consider those customers our nested customers, almost like a Russian doll of, that's how we describe it. But of course, we have to onboard our customers, and we have to do the same kind of due diligence, maybe even more strict, or depending on what their regulations are. But as a bank, you're very strongly regulated, and it's very important that, companies can't do business with you if they shouldn't be doing it.
Exactly.
So obviously that's deep, what's called IDMV, or identification and verification checks on the owners of those companies, and looking into their backgrounds, and many different checks that we do. So it's not a commercial bank, it's not a high street bank, it's not like HSBC or Barclays. It's a bank for other companies to build their platforms on top of.
Thank you very much, and very interesting. Thank you very much. There's no more questions. Then again, thank you, James.
Thank you.
Then we'll head over to our next presenter, Daniel. Welcome, Daniel, to Func Prog Sweden.
Hey, everyone. Thank you so much for having me here. And I'm going to try to pitch Scala to all of you in this talk about Scala and functional programming, and how Scala can be a purely fun language to work with. My job here is to demonstrate the nice features of Scala that make it such an expressive language, and hopefully at least one person in this room, or maybe watching this this presentation, might take away this lesson that, Scala might be such an interesting thing to at least try in a pet project before we spin it up at our day job or something like that. So welcome everyone to a sweet guide to Scala for beginners. I've been told that not everyone in this functional programming conference is a Scala developer. So hopefully we'll have a chance to talk about Scala for seasoned developers, but for people that haven't seen Scala before. My name is Daniel, and I am a software engineer and teacher. I've been teaching Scala for a while, and I've had the privilege of teaching more than 70,000 people all over the world at this point, and have the opportunity to train some high-performing teams at some of the the highest profile companies in the world, like Adobe and Apple and Microsoft and that sort of stuff. So I've been teaching Scala out of passion. I love this language, and I love the ecosystem and the tools. And I founded this website called Rock the JVM, which is a learning platform for pretty much everything in the Scala ecosystem, not just the Scala language, but functional programming, tools like CATS and CATS Effect, Apache Spark, Apache Flink, Akka, and so much more. So my job in this talk is to give you a glimpse of what Scala can do. And the way that I like to present and teach things like Scala is not so much with slides, although they do help with some diagrams that are impossible to demonstrate with just hand waving or in code. But my style is mostly live coding. So I'm going to attempt writing code for most of this presentation to just show you how Scala can be such an expressive language to work with. So without further ado, I have here a pretty empty project in IntelliJ IDEA. And I have here a simple Scala application with a main function. Those of you Scala developers or even Java developers might recognize this sort of structure. So this is pretty much a class with a static main function that takes an array of strings and returns unit, which is the Scala way of defining void functions. Scala is, as most of you, I'm pretty sure you know, there's a statically typed language, unlike Clojure. So the compiler does a lot of work for you and infers types and so on and so forth. So I'm going to demonstrate some of those functionalities as we go along. And this main function will be used just for us to test some stuff, just so we can see how things work when we actually execute them. So given no background in Scala, I'm going to try to explain at quite a fast pace some of the nice stuff about Scala and how Scala can help you think differently and approach code in a different way. And hopefully by the end of this talk, you'll get a glimpse of how you can extend functionalities of existing types, how you can write natural language like code, and just have the compiler do a lot of things for you and compile only for those pieces of code that you want to compile, therefore making the compiler do a lot of work for you to validate the correctness of your code. So this is the general gist or the general objective of the talk. Now, I'm going to start with zero knowledge of Scala prior. So we know about Scala that is object-oriented and functional in the sense that it blends the advantages of Java. So Scala was built initially for the JVM, which is object-oriented programming, plus the higher level functional programming principles on top of those. So we are going to also see how functional programming can be built on top of the JVM, which was originally built for an object-oriented language. Java is one of the canonical O languages. So in Scala, we tend to think of values and expressions. Values are essentially these constants that you cannot change. Of course, we have variables that can be changed with time, but the idiomatic Scala way would be to define values which are essentially unchangeable constants. So let's call this value meaning of life. And this meaning of life is obviously 42, as we all know. Now, the compiler can infer the fact that the meaning of life variable is of type integer. So I can write this type, but I don't have to write it because the compiler infers that for me. So we know that meaning of life is an int without us writing the definition for it. This makes a very powerful compiler because this speeds up our development process without taking the types out of our head and leaving them to the compiler to figure them out. Now, we tend to think of these as constants because we cannot change them. And we also tend to think in functional programming with values and expressions. So in my beginner Scala courses and trainings, I teach people that unlike the imperative style that they're used to write most of them, in Java or in Python or in C++ or in that sort of thing, we tend to think of code as instructions, like things that are executed step by step and making the computer repeat some stuff and do things conditionally and so on and so forth. But we tend to think in algorithmically, step by step. Rather, in Scala and in functional programming, we think in terms of constants or values and expressions that build upon these values to produce new ones. And our programs, our functional programs, are essentially one giant expression computing value. So expressions are everything in Scala, or rather backwards. Everything in Scala is an expression. Even if statements, even for structures are also expressions. Let me give an example. So if I define a val, let's call this if expression. This is, let's say, if 2 bigger than 3, then I'm going to return the string bigger, else smaller. So unlike other languages where we say if 2 bigger than 3, then do something, otherwise do something else, this whole bit is one expression, meaning that this can be evaluated or reduced to a value. This is the fundamental difference between an expression and an instruction. So in Scala, forcing constants and expressions naturally force us to think differently. So Scala and functional programming incentivizes us to think differently. And one easy way of thinking differently, with respect to simple code at least, would be to completely make do without loops. Because there's nothing to change, then there's nothing to loop for. So we say that loops can be simulated, or rather redone, as recursion. And functional programming experts will be masters of this. So recursion would look something along these lines. In natural, let's say, more common languages like Java, let's say if you wanted to sum the first n numbers, we would define a function, let's call this sum n, where we have an int n, and this returns an integer, and then we would say int sum equals 0, and then we would say for int I equals 0, then I less than or equal to n, something like that, and then we say sum plus equals I, and then we would say return sum. So this is the algorithmic step-by-step instruction-based thinking. But in Scala, we are forced to think differently because there are no variables. There are variables, but the idiomatic way of writing Scala code would be to ignore variables because, as functional programmers already know, variables make for some hard-to-read code, hard to understand, how to debug, how to reason about, and so on and so forth. So the natural expression-based way would make code much more understandable. I'm going to simply demonstrate how that works in Scala. So I'm going to define a sum n function that takes an n as an integer and returns an integer, but of course, because the compiler infers types already, I don't have to write that myself. So I can say if n is bigger than or less than or equal to 0, let me define the base case, I'm going to return 0. Otherwise, I'm going to say n plus sum n with n minus 1. So notice that at this point, we've defined a recursive function, which does pretty much the same thing. Now, for recursive functions, I do have to specify the types because the compiler will rely on the expression that the function will implement to infer the type, but because the expression already contains the function definition, the compiler is stuck in a loop. So I have to help it by specifying the type beforehand. That's just for recursive functions. So notice that in just one expression, I can compute pretty much the same thing as I did in an imperative style in Java. So Scala forces us to think differently. This is pretty much the first takeaway. And I think I wrote this in a different comment here. So think differently. Now, thinking differently involves a variety of aspects in functional programming and in Scala. And in this talk, I'm going to attempt to demonstrate a bunch of those, hopefully limited by time. So this involves a different mindset. Scala also has fully object-oriented programming in terms of classes, interfaces, extensions, inheritance, polymorphism, generics, and much more. So I'm going to simply give an example. I'm going to define a class person, and when you define a class in Scala, you also define its primary constructor right off at the bat. So here at line 28, this class person also has its primary constructor, let's say a name as a string, and a favorite language, or favorite programming language, of course, as a string, because every person must have a favorite programming language, of course. And you can obviously define methods and fields and so on and so forth, just like you can in other object-oriented languages. For example, I can define a method called likes that takes a conference as a string. And this one will return a string, but obviously the compiler can infer that, so I can simply implement that right off the bat. So I'm going to say s-quote, and s-quote is pretty much an interpolator. If you've done any TypeScript or JavaScript before, this allows injecting expressions or other variables inside the string so that you don't do the weird a plus space plus b plus space that we used to do in Java. So I can say name likes conference. So right out the bat, so we have the likes method returning a string. So if I hover over this, we know that the method returns a string. This is inferred by the compiler, and the IDE is smart enough to figure that out. Now, one nice thing about object-oriented programming in Scala is that Scala makes these sort of methods that take one arguments very nice to invoke. For example, let me define a val called Daniel as a new person with the name Daniel, and the favorite language, it's obviously Scala. Now, I can call the likes method on this person, so I can say Daniel Func Prog, Sweden, of course. I can say Daniel.likes functional programming Sweden, so Func Prog Sweden. And this is the natural dot notation that we're used to from the C family of languages like Java or JavaScript or C or C# and that sort of stuff. But with methods that take only one argument, you can also call it in a very natural language style way. So I can say Daniel Func Prog version 2 as Daniel space likes space Func Prog Sweden. And this is the exact same thing. So notice the natural language approach to calling methods. This only works with methods of one argument, of course, because if you have multiple arguments, the compiler can't tell whether you're chaining arguments or you're calling some other method, because of course you can chain them. So you can say Daniel likes Func Prog Sweden. What natural English almost code that is. Now, you can also have in Scala, we have very permissive method naming. For example, you can define non-alphanumeric methods. So I can say def may invoke some sort of symbol like triple exclamation marks, conference as string, and let's say that I'm simply calling likes on that conference so that I don't have to duplicate the method. This triple exclamation mark is a valid method name in Scala. And combined with this infix style, this is what this method notation is called, we can define something like this, like Daniel Func Prog version 3 as Daniel and then a space, and then I can call this new method that I like, which is triple bang, Func Prog Sweden. And this is for mathematical like notation for various abstract libraries like cats or cats effect. If you've heard of those, they use these sort of methods very, very often. So Scala and functional programming go hand in hand in this case, also because of this simple approach to method naming, because all our expressions can also be thought of as mathematical expressions. This is very, very nice in Scala, and this is not some rocket science that the compiler does behind the scenes. It just converts this infix style into the natural dot notation that the JVM understands. All right. There's also another method, another special method in Scala called apply, which is very, very powerful for functional programming principles on top of the JVM, as will become apparent shortly. So if I define a method called apply, so I'm going to say apply with, let's say, language as a string, and this return Boolean. And I'm going to simply return true if this language is equal to the favored language. So I'm going to say language is equal to favored language. Now in Scala, the double equals is the dot equals in Java. So this thing is automatically the equal sign in Java. And because we're using strings here, the equals method will obviously return the right thing for the right strings, even though the strings instances themselves might be different. So apply is special. So I can say Daniel likes Scala as Daniel.apply with Scala. And this, of course, is true, but the value of this method is not that important. The form is what's important. The apply method allows an instance of this class to be invoked like a function. So I can say Daniel likes Scala version 2 as Daniel invoked on the string Scala directly. Notice how powerful this little trick is. Once we've defined an apply method in a class, we can invoke that instance on a bunch of arguments. Of course, the apply method can be overloaded. It can have multiple arguments and so on and so forth. And we can simply invoke that instance on those arguments as if it were a function. Now, this is a very powerful trick because this allows functional programming on the JVM. Now, before we deal with functional programming on the JVM, I just wanted to mention the fact that Scala also has the traditional object-oriented features. So we have abstract classes, we have inheritance, we have interfaces. In Scala, they're called traits. We have generics. We have polymorphism. And the natural things that we know from canonical object-oriented things like Java. Now, switching to functional programming on top of the JVM, we know from experience that functional program, and also from the definition of functional programming, of course, that functional programming's objective is to be able to work with functions as quote-unquote first-class citizens. What does that mean? First-class citizens means that we want to work with functions like with any other kinds of values in our programs. So we want to work with functions like we do on numbers, on instances of classes, and so on and so forth. So we have to be able to compose them. We have to be able to pass them as arguments. We have to be able to return them as results. We simply need to be able to associate them to variables. Now, how is this principle going to work on top of the JVM? Well, the JVM was built for Java, of course, and Java doesn't have this notion of first-class functions. Obviously, it does have Lambda functions, but that's not necessarily a first-class thing on top of the JVM because you can't associate or you can't work with these sort of lambdas like you would in a purely functional language like Scala. But the way that Scala implements the functional programming ideal on top of the JVM is to define these sort of special traits called function 0, function 1, function 2, function 3, and so on and so forth, and grant them this apply method, which gives them the ability to be invoked like functions, of course. Let me give an example. So I can define, let's call this multiplier, as a new function, let's say function 2 that takes 2 arguments. Notice that we have function 1, 2, 3, 4, 5, 6, 7, and so on and so forth. So we have special traits that are built into the Scala standard library. Function 2 takes a bunch of type arguments. So these square brackets are the equivalent of angular brackets in Java, the generics in Java. So I can say int that so these are the quote-unquote arguments of the function. And the third type argument is the return type. So new function 2 with int, and function 2, because it's a trait, I can instantiate it on the spot with anonymous classes. So I can override the apply method. So function 2 has this fundamental method called apply. Let's call the arguments x and y, then actually called v1 and v2 because they were generated. So I can say x times y, for instance. Now I'm going to collapse this code because the implementation is not that important. What matters is that this multiplier is an instance of a type that the JVM understands. Now, of course, I can say val, let's call this 12, as multiplier dot apply, because that's the fundamental method of the function trait. And I can say 3 and 4, and obviously I'm going to return the number 12. But because the apply method is special, as I've just described, we have, let's say, 12 version 2 as multiplier invoked on 3 and 4, which makes this multiplier thing pretty much be a function. So the functional programming ideal was based on a very simple trick. Just create function traits in the standard library and grant them this apply method, which gives them the ability to be invoked like functions. And because this is just an instance of a type, much like any other type on the JVM, you can pass it around. You can pass it as arguments, you can return them as results, you can combine them with any sort of methods, you can write any sort of thing with these types. So the functional programming principle of having functions as quote-unquote first-class citizens is implemented on the JVM with these function types with apply methods. Now, if this isn't quite magical and this is a quite simple trick that the compiler can work, then I'm going to back off. I don't know what else can be magical on top of this. So functions, these function types are traits, also known as interfaces in Java. All right. Now, we can also define, or rather, Scala defines type sugars for function 1, function 2, function 3, and so on and so forth, because typing this sort of stuff is quite tedious. So I can say val multiplier version 2, and this is of type int, arrow, int, which is syntactic sugar for the same function 2 type. So if I remove int, arrow, int with function 2 type, these are exactly equivalent. So I'm going to keep it like this. And I can say x, y, arrow, x plus y. So the kind of syntax that you're familiar with from other functional programming languages, or even from the object-oriented languages that brought in functional programming elements. So you know this kind of syntax, x, y, arrow, x plus y. But Scala goes a little bit further than that, and a bit to the extreme, if you can read such compact code, I can say multiplier version 3, again as the type int, arrow, int, and I can say underscore plus underscore, which is pretty much the shortest lambda that you can possibly write. Each underscore means a different argument. So if you don't really need to use these arguments more than once in the implementation, all you care about is the expression itself. And this is the rawest form of expression that you can possibly have. It's like just writing plus in Clojure or in Haskell or that sort of stuff. All right. But of course, the writing something like plus doesn't quite work. In Scala, you have to use this sort of syntax, which is pretty damn close. So notice that Scala has all these kinds of sugars and tricks that make it a very expressive language and a natural functional programming language on top of the JVM with these sort of tricks that I've just described. All right. Cool. So these are essential functional programming elements on top of the JVM. Obviously, in a course or in a training like this, I would spend pretty much half a day just talking about this and what the kind of higher order functions that Scala supports and so on and so forth. But I think you got the idea. The goal of this presentation is just for you to get some principles and some ideas of how Scala works. Obviously, we have the map, flat map, filter, and so on and so forth that you see in other functional programming languages. So for example, I can say a transformed list as list apply to 1, 2, 3. So when you say list invoked on 1, 2, 3, obviously this is the apply method, because you now know that the apply allows this thing to be invoked like a function. So list 1, 2, 3. And then I can say map, and obviously then I can do a transformer on every element. So I can say underscore plus 1, let's say, and this will be the list 2, 3, 4 as we can probably expect. So we have list123.map, and this expression is obviously a lambda that you can write in this very shorthand form, or you can say x arrow x plus 1 if you'd like to be more explicitly, or if you want to be really verbose, although I've never seen this happen in practice, with a new function 1 taking an int and returning an int where the apply method is whatever. All right. So everybody writes something like this because it's very easy to understand. And when you look at a one-liner like this, after 5 minutes of learning Scala, you know what it means, and you can read it very easily, which means that Scala is a pretty readable piece of code. So when you write 20, 30 lines of Scala, they can do a lot because the Scala code is very compact, but you can read them very easily. It's quite natural to see that this is a transformed list. I can say, let's call this a bigger list as list 1, 2, 3, and then I can do flat map. So flat map takes a function from an element to a mini list. Let's say list and x plus 1. And flat map, I'm not sure how big of a functional programming background this audience has, but assuming that you're watching this video and you have no idea how flat map works, FlatMap takes every single element of this list and runs this little function, which basically turns each element into one mini list, and all the mini lists are combined into one. So in this case, we have a list composed of 1, 2, because this is the mini list obtained from element 1, then the elements 2, 3, the mini list from element 2, and then 3, 4, the mini list from the third element. And these are compacted into one. Now, map and flatmap in Scala have the capacity of being combined into chains because that's a useful programming pattern, and this happens all the time when you process collections, when you process streams, when you process any other data types that have map and flatmap, for example, effects or monads. I know we have a monad tutorial or a not monad tutorial at the end of this meetup, so I'm not going to go there too far. But map and flatmap will allow us to write a very special structure in Scala called a for comprehension. So let's call this checkerboard. And in this checkerboard, I'm going to combine two lists, let's say a list of characters and a list of numbers, and I'm going to obtain all the combinations between them. Now, in Java or in an imperative language, we would have to do a double for loop and combine every element with every other element and so on and so forth. But in Scala, we would have to write something like this. Let's say list A, B, and C, and then I'd say flatmap, because for every little element, I'm going to return a mini list. So I'm going to call this character. And then I'm going to say list 1, 2, 3, 1, 2, and 3. And then I'm going to call map on every number. And then I'm going to return an S-interpolated string, let's say character dash number. So for every little character, I'm going to return all the combinations between 1, 2, 3 and that character. Of course, once you've exhausted the characters, we've obtained all the combinations between all the characters and all the numbers. And in main, if I do a print line, so if I do a print line, and I'm going to use this checkerboard thing, if I run this application, we're going to see all the combinations between the characters A, B, C, and the list 1, 2, 3. So we have A1, A2, A3, B1, B2, B3, C1, C2, C3. But the map and flatmap chains in practice can get quite long. So in Scala, we have this magical expression called a for comprehension. So we have this checkerboard. I'm going to use checkerboard version 2 as a for comprehension. So this is not a loop. So I'm going to write this in all caps for everyone to understand. This is not a loop. This is an expression. And I'm going to tell you what kind of expression it is. So I'm going to say car in list with A, then B, and then C. And then I'm going to say number in list 1, 2, 3. I'm going to say yield. And I'm going to use this sort of expression car dash num. So I'm going to paste it here. And this checkerboard version 2 is exactly the same as above. Now, not similar, it's identical, because every for comprehension in Scala is reduced to a flatmap and map chain. So whenever you see a for comprehension in this way, which is far more readable for us as usually imperative programmers before we turn functional programmers, this for comprehension is actually turned by the compiler into map and flatmap chains. So if I do print checkerboard version 2, then this will give us back the exact same result. All right, so we have the list A1, A2, A3, B1, B2, B3, and C1, C2, C3. But the for comprehension is far more scalable in terms of code, because you can simply add another generator here, another line, and then you combine 3 lists and then 4 lists and so on and so forth, rather than writing flat map all the way. All right. So for comprehensions are incredibly powerful in Scala, and this is pretty much a syntax sugar for map and flat map chains. Now, I hope I've convinced you that at least for essential code, Scala is a pretty powerful and expressive language, which turns very compact code into something that's very powerful and does a lot of things behind the scenes, without sacrificing readability, of course. One magical aspect of Scala, there are multiple magical aspects of Scala, but one truly magical aspect of Scala is called contextual abstractions. Contextual abstractions are a set of features in the Scala compiler that will only allow you to compile your code under certain conditions, and the conditions are yours to control. For example, I'm going to write something along the lines of a sorted list. Let's call this a sorted list as list, let's say 4231, and then I'm going to call sorted. Sorted only compiles for things that already have an implicit ordering. That means that there has to be somewhere defined in other pieces of code that you can import a value that can compare 4, 2, 3, and 1, the integers. The Java analogous to that will be a comparator object. Comparator, I think. The way that this works is that we have 4, 2, 3, 1, and that comparator is passed automatically at the sorted method. So if I print this sorted list, we will see the natural order of integers being shown in this list. So we'll see the list 1, 2, 3, 4. Now we can control that. We can say a given value. So the given value is kind of like an automatic thing that the compiler can inject into this sort of method. So let's call this automatic ordering, and this is of type ordering int. This is the kind of analogous to comparator in Scala. So I'm going to build one. So I'm going to say ordering from less than. I'm going to use underscore bigger than underscore, returning true between these two numbers, saying that one number should be before the other if it's bigger than them. So this is what this lambda is supposed to mean. Natural integer ordering looks like this, but the descending order looks like this. So I'm going to simply define an automatic ordering as a given, not as a value. Once I've defined that as a given, if I run the exact same code with absolutely no modification, we're going to see the list 4, 3, 2, 1. So this automatic ordering is being passed automatically. So automatic ordering, automatically, of course. We call that implicit. So we used to call these sort of values implicit because there is an implicit keyword in Scala 2. I'm writing Scala 3 as we're recording this video. So those of you watching from other sources like YouTube and seeing this in posterity, this code is written in Scala 3. So this is the latest incarnation of the Scala language, and the keyword for that is called given. And this given is passed automatically to the sorted method. If you carefully look at the sorted method signature, we have this keyword implicit ordering B. This means that the compiler fetches whatever given value there is in the scope and passes it automatically to this method. Obviously, you cannot create two givens for the same type because the compiler will not know which one to pick. All right, so this was the first contextual abstraction. One is called given. Now, the given values that are being passed automatically go in tandem with using clauses. The implicit keyword that you saw earlier was from Scala 2, which still works in Scala 3 for backwards compatibility reasons. But in Scala 3, the implicit keyword was so widely used for different purposes that the designers of the Scala language decided to split the meaning into multiple words. So the keyword now is using. So I'm going to define, let's call this method with automatic argument. I'm going to pass an argument as a string and the automatic value with a using clause. So let's call this amount as an int. This returns a string, and I'm going to simply repeat the string n times. So I'm going to say arg times amount. The times operator works like in Python. Now, I can call this method with automatic arguments. So I'm going to say method with automatic argument with the string Scala, but the code will not compile. So here I have a compiler error because the compiler could not find a given value of type int that it can inject automatically. So you are the one to control which automatic values you can pass or whether you want to pass them at all. So this will pretty much help you prove the correctness of your code by controlling which using clauses you want to satisfy. So I can define, let's say, given, let's say, automatic int as having the type int, and let's assume I'm returning the string 3 so that we don't repeat the string Scala too many times. So now that I've implemented this given thing, then I can pass that automatically, or rather let the compiler pass that automatically for me. So if I print this in main, so if I do print line with method with automatic argument, then I'm going to see Scala being printed 3 times. I'm going to show you one other magical thing of Scala, and then I'm going to stop. So the second magical thing is extension methods. Extension methods have been around in Scala since I think since 2012 or something like that, so well more than a decade now. And JVM languages like Java have yet to catch up with this concept. Extension methods will allow you to add new methods on types that do not have those methods. So for example, I can extend the int type, so I can say extension with n as an integer, and I can say def times with an s as a string, and I'm going to return a string and say s times n. So I'm going to do the same thing, repeating that string n times. Well, in this case, I'm going to say Scala times 3 as 3 dot times with the string Scala. So the times method now exists on this number. And this number means, the existence of this method means that I can now enhance my code with things that are more expressive. So I can say 3 times Scala. I can also call that infix, which makes it as close to natural language as you can possibly expect. So obviously, if I print this in main, I'm going to see a very similar result. So we have the string Scala repeated 3 times in the fabulous console. Now, these extension methods, as well as given and using clauses, so 1 plus 2 will yield some powerful abstractions. For example, type classes. Type classes are an extremely powerful concept in functional programming that will only allow you to invoke certain functionalities on certain types and not others, and make the compiler not compile your code if you're trying to invoke those functionalities for types for which you have not implemented type classes. And this leads to more expressive code and more modular code. Now, I would be absolutely happy to demonstrate type classes, but this will probably take another half an hour. So I'm going to stop here, and I'm going to simply invite you to join me at rockthejvm.com. This is my website. This is where I teach everything in the Scala ecosystem. Now, I'm happy to take any questions that you might have for me.
Thank you very much, Daniel. Super nice presentation. I really love that you made like a presentation, coding and explaining the concepts and really showing like this is the steps. This is what you can do. Super nice presentation. I have one question that came up. Maybe you can or you can't answer it. Like, how does Scala compare to Elixir?
I have no idea.
No.
I have not touched Elixir, so I cannot really say.
Me
I do
neither,
have something to say
unfortunately.
with respect to one particular set of libraries in the Scala ecosystem. It's called Akka, and Akka basically implements the Erlang model of actors, so that you can design your program in terms of these entities called actors that can exchange messages asynchronously. So in that sense, the Akka set of libraries will pretty much resemble the Erlang model. So you can design clusters of systems that can communicate asynchronously, regardless of whether those actors run on the same machine or on distributed systems, and so on and so forth. And there are a variety of tools based on them, such as streams and HTTP servers and cluster sharding and that sort of stuff.
Yeah, we have had a presentation, I think 1.5 or 2 years ago, exactly around Akka or Scala and Akka. As you say, very alike to Erlang type of thinking and doing things. Let me see. No, I don't have any more questions. As I said again, very nice presentation. I really liked it. It's really good intro, both to functional programming, but also to Scala. I'm not that into Scala myself, but thank you very much. Now I know more. So
that was my goal.
Yes, now I know more. You will find the links, and we'll post them to your channel at Rock the JVM. And we'll post everything below the video once we put it out, so people can find more introductions and presentations if they want to know more about Scala and your presentations and the stuff you've done.
Sure, and if anyone has any sort of questions about Scala, or if you're interested in taking any sort of training or course, just reach out to me at Daniel@rockthejvm with any sort of questions related to Scala. I'm more than happy to help. And I'm active on Twitter @rockthejvm, on LinkedIn, on YouTube, and everywhere. So you can check out my stuff at rockthejvm.
For sure. People, take a chance. Ask Daniel. Again, thank you very much.
Thank you.
with that, then we go over to our next presenter. He's not in as yet. Yeah, we might take like a 3-4 minute break and we'll come back. Well, what do? You live stream, you don't know what's happening. Daniel, welcome back.
I'm here.
As we have you still on here, what would you show next? What would be the next concept to show or talk about in Scala?
Well, I could show you type classes, which is built on top of these magical features that I ended up with in my presentation. If you want, or until the next speaker comes up, I can start to do some demos.
Oh, do some demo. I would love some demo. If you have
really? Okay.
If you have some ready demos.
All right. Well, let's do this. Let me share my screen again, and let's get back to where I ended up with. So we were at contextual abstractions with given instances and using clauses and extension methods. All right. Good. Extending the live talk to type classes. Okay. Let's talk type classes. What are type classes? I mentioned earlier that type classes are a way to design your program in the sort of capability managed by the compiler. What do I mean by that? We would like the code to compile only for those types that have this sort of functionality, and we would like the code to not compile otherwise. So let's define some sort of example to motivate the need for type classes. Let's define a small library to transform data into, let's say, HTML. So we would like to transform data structures into HTML with some sort of serialization library. So the version 1 way, or the natural object-oriented way, would be to define a sort of trait, and we would define the sort of extensions or inheritance-based code. So I would say HTML writable, where we would have a method called toHTML that returns a string. And all our data types that we would like to convert to HTML extend this trait. So let me define a case class. So a case class is kind of like a data class, kind of like a record in Java, except Scala was doing that 15 years earlier. So hashtag brag. Let's call this user, which has a name as a string, an age as an int, and let's say we have an email as a string. This would be a user in our application. Let's say we're building a social network or things of that nature. And this, in the object-oriented way, would extends HTML writable. So we would have the toHTML method. So I'm going to say override. I'm going to override to HTML, and I'm going to use an S quote. I'm going to do a div, and I'm going to put that close. I'm going to do a name, and I'm going to say age, years old, and then I'm going to have a link to their email, and I'm going to say a href equals, and I'm going to use mail to, and I'm going to use email, things of that sort. Now I need to escape this stuff. So I'm going to say mail to email, and then I'm going to close my little tag here with a slash, not with a backslash. All right, I'm not a front-end developer, so excuse my poor HTML skills. You get the idea. So all our data types in the object-oriented approach would have to extend this sort of trait. Now, those data types that do not extend the trait do not get this functionality, which means that if I define a val called Bob as a user with, let's say, Bob and age 45, and this email bob@rockthejvm.com, we would say Bob to HTML as bob.toHTML, of course. So we only have this method for those data types that extend the major trait that we want to implement. But this comes as with major disadvantages. So I can define some drawbacks. For example, this is only available. Let me scroll down to see my comments. So this functionality is only available for the data types that we support. Adding a new data type will crash our entire thing because our data type is not an HTML writable. So if we are handling the sort of server-side rendering to our front end, we want all our data types to support HTML writable. So we would like to, we have to support HTML writable for all our data types, but our data types might also have other functionalities which might conflict with this sort of thing. So this is only available for data types that we support, and we can only provide one implementation. So if we ever want to change the implementation of HTML writable, we would have to change the implementation everywhere on all the data types, which is a terrible thing to do. So this is tedious. This leads to bugs if we ever change our code base and so on and so forth. That was version 1, the object-oriented way. There are a bunch of other versions. Let's say version 2 with pattern matching. So we would have an object, which is essentially a singleton in Java terms. I'm going to call this HTML serializer. Let's call this pattern matching. And I would have to define a method. Let's call this serialize to HTML, and this will take a value. But because our values can be of arbitrary data types, because our data types might not necessarily be related, we have to support the any type, which basically destroys our type safety, because the any type can support anything. It can support integers, strings, and even data types that we do not want to support. So this would return a string, and I would say value match. And in case we get a person with a name, age, and email, then I'm going to return this sort of S-interpolated string, not a person, but a user, with a name, age, and email, and so on and so forth. And in case we get something else, we would throw some exceptions. So new, illegal, argument exception, let's say unsupported data type, which pretty much makes it a nightmare because we also need to handle illegal argument exceptions all around our code base. So the drawbacks to this are that we've essentially lost type safety. So lost type safety. We still have one implementation for everything, because all functionality is pretty much crammed in this object. Modifications are terrible. If we ever need to modify the implementation or to support a new data type, we would need to modify this entire code base. I would honestly be afraid to touch this code. So this was version 2 with pattern matching, which is again a Scala feature, but this doesn't really work that well in this case. So enter version 3, which is type classes. And type classes are nothing but pretty much a design pattern in order to organize your code and modify or split the functionality in such a way that you can extend the functionality easily. But I think I'm hearing myself. All right. So we would like to decouple our code from the definition, the implementation, optionally provide multiple implementations, and make it easy to change what we want to support and how we want to implement that functionality. Let me give you an example. So let's say that we would like to implement the type class pattern for this sort of functionality. We would like to define a simple HTML serialization library that turns values into strings, let's say. So I would define a trait. Let's call this HTML serializer that takes a type argument. Let's call this A. And this has a single value. Let's call this serialize. So serialize value of type A, and this turns that into a string. So this is, as I discussed earlier, this is like generics in Java. Serializer with angular brackets A, and once you've defined the type A, you can use it in the body of HTML serializer. Now, this is part 1 of the type class pattern. Part 1 is just to define the type class. So the type class contains all of the types. So this is how I want you to think about this. HTML serializer contains all the types for which we have the serialization capability. So turning values of those types into strings. Now, we would support certain types and not others through part 2, and that is type class instances. So I would define something along the lines of a val, let's call this user serializer, as a new HTML serializer of type user. And I would need to override the serialize method. So override serialize that takes a user and returns a string. And I'm going to simply decompose that. So I'm going to say val user with name, age, email is equal to value. So this is the kind of pattern matching deconstruction that you see in Python. For instance, you can deconstruct a tuple just by defining 3 variables into 1 line. And then I'm going to return the appropriate string. So this is what we call an instance of the type class, because this is a piece of functionality that implements the serializer for a particular type, which is user, and then we can use it later in external APIs. Except, I'm not going to keep it a val, but I'm going to make it a given. A given means it's automatically being passed by the compiler to whichever method requires an HTML serializer of that type. So I'm going to say HTML serializer of user. So I'm going to have to add the type here, because otherwise I'm going to get a compiler warning. And notice that this code turned into gray because the Scala syntax will allow some shorter code. So I'm going to say with this sort of implementation. So this is essentially the same thing. So instead of making it a val, I'm going to make it a given so that this value is being passed to whichever API requires an HTML serializer of user. And that is part 3, the external API. So I'm going to, in part 2, you can define new HTML serializers for whatever data types you want to support, for users, for blog posts, for likes, for whatever. You can pictures. So here is where you define type class instances. So all the types that you want to support each have their own implementation. So notice how easily it is to decouple the definition from the implementation. Now, the external API would look something along these lines. I'm going to define an object. I'm going to call this HTML serializer. And this is a singleton object that is called a companion of this trait. There are a bunch of properties with these things, but just I'm going to create this singleton object that I can use as a static instance, as static methods in Java. And I'm going to define a method called serialize that takes a value of type A. And I'm going to have a value of type A. So this is the external API. I would like the serialize method to only allow those types for which there is a using clause. And I'm going to call this HTML serializer of A. And this returns a string. And the implementation of this method is not really that important. So I'm going to use serializer.serialize on that value, but I'm going to collapse that because it's not important. I want you to hide that away. And whenever I want to call this serialize method, this will only be possible from the compiler's point of view, only for those types for which there is a given value of this type in scope. For example, I can say HTML serializer.serialize on Bob. Bob being my first user. And this compiles and runs because we have a given HTML serializer of user in scope. So in this case, I can run this code and we'll see the same HTML as we expect. So notice we have div Bob 45 years old and so on and so forth. So we have the server-side rendering available for Bob, but, and this is the most powerful aspect of type classes, I can say HTML serializer.serialize, and if I pass in a regular value like 42, this doesn't even compile. Not only does that not run or give this some sort of bug or error, but the compiler prevents you from compiling this sort of code because the code is guaranteed to be incorrect due to the fact that you don't even have a serializer for that particular type in scope. So unlike the previous implementations where we used to throw exceptions and catch them, and we have this sort of spaghetti kind of code, hard to debug, hard to understand, hard to touch, hard to modify. In this case, the compiler is our friend because the compiler doesn't even compile our code. Not only that, but we can extend this sort of type class functionality with an optional part 4, which is extension methods. So I can define, let's say, an object. I'm going to call this HTML syntax. And I call this syntax as a good practice in functional programming libraries with extension methods because we are essentially adding new pieces to the Scala language in this case. So I'm going to say extension, and assuming we have a type A and a value of type A, I'm going to define a method called toHTML that requires a using clause, so a using serializer as an HTML serializer of type A, and this returns a string. And the implementation is, again, not important. I'm going to use serializer.serialize on that value. So again, I'm going to collapse that. So once we have an HTML serializer in scope, we can say, and this is pretty magical, I'm going to say print line bob.toHTML. But this is only available if I import HTML syntax dot everything. And notice that once I've imported HTML syntax star, I have access to the toHTML method, which is only available for the right types. So only available for the right types. That is, those for which we have a given this sort of stuff in scope. And again, if I try running this sort of thing with the wrong type, like Scala.toHTML, this doesn't compile. toHTML cannot be used as an extension method. So this does not compile. So notice how flexible our code became because we untangled the definition, the implementation, and the API into one triad, which is the type class pattern. So this was the demonstration that I have for type classes. I hadn't prepared this earlier for the presentation, but I hope this makes sense given the magic that Scala has under the hood.
Thank you very much, Daniel, for just going in and giving yet another cool like definition and showing the power the power of Scala. Really nice. Thank you very much again, Daniel.
My absolute pleasure.
Yes, you will. Thank you very much. With that, thank you. We have the next presenter online. Welcome, Yehonathan.
Hello.
Hello, and welcome to Func Prog Sweden.
Thank you. I'm happy to be here with you.
Yes, and we'll head over to your presentation, Data-Oriented Programming.
Right. How much time do I have?
You have 45 minutes.
45 minutes. Okay. Should be enough. And can you see my screen?
Yes.
All right. I'm setting myself a timer. 45 minutes. Great. So I'm here to talk about data-oriented programming, and I happen to have written a book on the topic, a physical book that is available also as an ebook, but also as a regular book with, regular paper. And I'm here to tell you what is data-oriented programming, where and when it is relevant, and why it is a good choice, and especially how data-oriented programming allows us to reduce the complexity of information systems. My name is Yehonathan, and you can follow me and reach out on Twitter under the handle VIEBEL. All right. I've been a developer for a long time, maybe too much time, around more than 20 years. I wrote a book called Data-Oriented Programming. I'm a blogger. I work as a closure wizard at Psychognito, and I'm the maintainer of a cool open source JavaScript plugin called Clips that allows us to evaluate code right in the browser. Okay, so I said that data-oriented programming allows us to reduce complexity. So I guess it's time to tell you what I mean by complexity. And in fact, in programming, we have two kinds of complexity. We have the computational complexity, which is about the amount of machine resources required to run a program, how much memory it takes, how much CPU it takes, etc. But we are not going to talk about computational complexity. Instead, we are going to talk about system complexity. And system complexity has to do with the amount of brain resources it takes to understand a system. And our goal is to reduce system complexity. And I found a really nice quote from 1986 from a book called SICP, Structure and Interpretation of Computer Programs, that goes like this. Programs must be written first for people to read and only incidentally for machines to execute. And in fact, nowadays, it is so easy to make a program work or even to scale a system, by just scale the number of instances on the cloud. But the number of instances in the cloud does not allow you to develop more quickly. And if your system is complex, even if you hire more developer, it's not sure that you will be able to deliver more quickly. So that's why I think it's super crucial to write code in such a way that complexity is not increased too much. And I'm not going to claim that data-oriented programming is a good fit for every kind of systems. I think it's a good fit for information systems. By that, I mean systems that manipulate information. For example, web services, they access the database. They fetch data from the database with a shape, and they transform a bit the data maybe, and then they serve it as JSON. That's an example of a web service. Web workers that listen to events and reach them and transform data through a pipeline. Or even maybe front-end applications that have to manage application state, and they receive data from the backend, and they generate data back to the backend according to user interaction. So those are examples of information systems. Let me give you examples of systems that are not information systems. For example, a compiler, or I don't know, a game engine, stuff like that. And an important characteristic of information systems is that the program is not the owner of the data it manipulates. Usually the data lifetime goes beyond the program. The program takes data from another service, from a database, from a backend. And when data is not yours, you have surprises sometimes. And data-oriented programming allows us to write our code in such a way that we can manipulate data in a flexible way. So what is data-oriented programming? In fact, if I would need to summarize it in a short sentence, I would say it's a programming paradigm that treats data as a value or as a first-class citizen. And what does it take? It takes, in fact, to follow 4 basic principles. And none of those principles are new. They are well known to developers for decades. But I think data-oriented programming, the novelty of it is that the fact that it combines them together as a cohesive whole. And we will drill down later in the presentation in each of those principles. Let me just mention them briefly for the moment. Number 1, we separate code from data. So unlike in traditional object-oriented programming, where data is encapsulated in classes, data is a first-class citizen. It has the right to live on its own, even without code. Number 2, we represent data with generic data structures. Data has the right to be created with no ceremony, with no class, with no types, with no structs. We are allowed to create data on the fly. Number 3, data is a value, so values never change, like numbers. So we don't mutate data. Instead, when we want to change data, we create a new version of data without affecting the current version of data. And finally, number 4, we separate data schema from data representation. There are ways to validate that our data conforms to a schema. We have ways to validate data, and it's very important. But we have the right to decide when and where we want to validate data. So we have the right to create data that is not validated. Okay, before I explain how and why those principles reduce the complexity of the system, let's think about what usually makes a system complex. And for that, I'll take as an example online library management system. You know, a system where you need to manage books, lendings. Books are in a catalog. Books have authors. There are users. There are administrators, etc., etc. A standard information system. If you are not super advanced object-oriented programmer, you'll probably come up with a class diagram similar to the one on the screen. So multiple entities, librarian, user, catalog, book, author, book item, etc. And from my experience, usually traditional object-oriented programming systems tend to be very, very intertwined. All the objects are related together. There are many, many rows, many edges, many connections. And it makes the system complex because we tend to have nodes with many edges. And also we have many kind of arrows. You know, we have association, we have composition, we have inheritance, we have usage, and it makes the system how to understand and how to maintain. So first thing that we are going to do is to separate code from data. Code will be written either in stateless functions or in classes with static methods only, no state. And data, at this point, it could be represented as a data class, meaning class with only members, no methods, or records, or as the previous speaker mentioned, case class in Scala, or even string maps. So let me show you how we will represent data in a language like JavaScript. So we will have a class called book, and we have a constructor that receives a title and a publication year, and we have two members, title and publication year. Another option, as it is available in Java since Java 14, I think, a record or a case class in Scala. And third option, a string map. For example, in JavaScript, we have this curly brace literal to create string maps on the fly. And what about code? So code, we could either have it in a class, but if we want to have in a class, we need to constrain ourselves to static methods. So for example, let's say we need the functionality to retrieve book information from a book. So a nice little string that describes the book. So we would have a book info method that receives as an explicit argument the book that the method needs to manipulate. There is no this, no self, no state. And if we prefer to write functions, again, function without state, no lexical scope, just function that receives the book as an argument. And why does it reduce system complexity? For the simple reason that if you take a complex graph and you split each node into two, where on the left side you have the node that takes the code part, and on the right side the node that takes the data part, then instead of an entangled system, you have two simpler systems. And our brain is made so that it's easier for us to understand two simple systems than one complex system. Okay, so that was principle number one. We separate between code and data. Principle number two deals with how do we represent data. And because data is a first-class citizen, data is a value in data-oriented programming, we want to represent data with generic data structure. What do I mean by that? Basically, it's string map. And in JavaScript, we have two ways to create string maps. We have the map constructor, where we need to pass the fields as tuples with the key of the field and the value of the field. Or we could use the literal for map. In JavaScript, it's called object, but in fact, it's a map. So depending on the language, if it's Java, if it's Scala, Clojure, Ruby, whatever, you could choose one of the two. But no matter which one you choose, both of them are generic. Generic in the sense that you don't need to declare a priori the type of the data. You don't need to create the blueprint or a struct or a class that says how you are going to instantiate your data. You have the freedom to instantiate data on the fly. And in principle number 4, we will explore how we can validate data, even though it is created with, it is represented as generic data structure. So for the moment, let's put validation concerns aside. And let's see why, in terms of complexity, it allows us to reduce system complexity even more. Because in fact, we don't have the class diagram on the right. This diagram is only in our head. It's not part of the program. We have the freedom to manipulate a book, even without importing the definition of the book data, struct, class, type, or whatever. Moreover, when data is represented as data, we can visualize the whole system data, you know, just as a data tree. We can dump it to the console. We can send it over the wire. We can manipulate it with generic tool, visualization tool. Serialization is not a concern at all, because in every language there is generic data. There are generic universal libraries that allows you to take any hash map and convert it back and forth to a JSON string. And when we need to do data manipulation for our business logic, we have a plethora of data manipulation functions like sort by, group by, select, rename fields, pick fields, omit fields, etc. In fact, there is no need for reflection, because we can access any data members or explore the map fields just by using regular functions. So it makes our system less complex and more, and because our data model is more flexible and we don't have to commit to rigid data model, we develop more quickly. Principle number 3 is about mutation. In fact, we don't want mutation. And when there is no mutation, lots of bugs simply do not occur. We don't have surprises. We don't have any thread-safe concerns, because data is read-only in a sense. We don't have side effects. We write pure functions, and pure functions are easier to test, easier to maintain, easier to reason about, easier to predict, etc. The only problem is, what about performance? Do we clone each time we need to somehow manipulate our data or modify it a bit? Do we copy and write? Do we use special data structures? And here is the answer. So we have two options: either to use a special data structure, but in many cases we don't need a special data structure. We can use the standard native hash maps. And let me tell you how it works. And it is performant because we use a trick called structural sharing. So let's imagine that in our library, we have, that's the data structure, the data shape of our library. We have two fields, catalog and user management. And user management, we have lots of stuff. And in catalog, we have also authors and books. And in books, we have many books, and one of them is Watchmen with 3 fields. And let's say we want to modify one field in a book. For example, the publication year of Watchmen inside the books by ISBN, inside the catalog. So we want to update the value associated with this path. And instead of 1987, we want to update it to 1986. And when I say update, I mean I want to create a new version of this hash map where there is a single change, 1986 instead of 1987. So one trivial and brutal option would be to deep clone the library and modify only the new version. But there is a wiser trick that we can do, and it's called structural sharing. And for that, we create a new node library. And in this new node, the pieces of data that are not affected by our change, we just copy a reference to them. For example, in our case, the user management is going to be common between the two versions because we modify only the catalog. So we copy a reference to user management, and that's cheap. No matter how deep the hash map tree under the user management, copy a reference is a single operation. So it's fast and quick, and it doesn't take memory, it doesn't take computation. It's performant. But the catalog, we cannot copy a reference to it because we need a change in the catalog. So we create a new node called catalog, in which we copy everything beside the subfield that we need to change, the book by ISBN. And book by ISBN, we create a new node where we copy all the books beside one book, Watchmen. And Watchmen, we create a new node where we copy all the fields from the previous Watchmen book beside the new field that we want to change. So the vast majority of the nodes are shared between the two versions. And because data is immutable, it is safe to share. We don't need to ask ourselves, what about if someone changed the field in the one field under user management? Does it affect the two versions of the data or only one version? This question is irrelevant because data is immutable. And as I said a moment ago, when data is immutable, it's safe to share it. But there is a little problem with this approach, is that sometimes we could have many references to copy. For example, let's say in books by ISBN, we have 1 million books. We would need to copy 1 million minus 1 references. And sometimes it is not affordable. So if it's the case, we can use a special data structure called, we could use a special data structure called persistent data structure that were promoted by Clojure in 2009, but nowadays it's available in virtually any programming language by third-party library. For example, in JavaScript, we have Immutable.js, developed by Facebook. In Java, we have Paguro. In Go, we have PEDS. In Clojure, it's part of the language. In C#, we have F#'s collection. In Python, we have Persistent. In Ruby, we have Hamster. And I'm quite sure that in Scala, it's provided by the language also. In Clojure, that's that all the data structures are persistent. In Scala, you can choose if you want mutable data structures or immutable data structures. Okay, so that was principle number 4. And principle number 4 says that we do not manipulate data. So up until now, you might ask yourself, okay, that's nice if I want to write a little program, that's a few lines of code. But for a real program, I cannot afford to live in the wild and to live without data schema. So what about data validation? And let me show you the kind of problem one could have if they don't do data validation. So let's go back to our book info function that receives a book with no type and returns a string based on the book. And in order to return the string, we access the title property of the book and the publication year property of the book. What happens if I pass by mistake an invalid book where instead of title, it is the title? Maybe the user types this mistake, or maybe there is a bug in the front end that sends an invalid request to the backend. Who knows? So what happens if I call book info with an invalid book? No error, but I have something very strange. Instead of an error, I say was published in 1986. So it silently fails. And this kind of bugs are very, very hard to track and to fix, or mostly very hard to detect. And the user will not get any notification that the request failed. So that's really, really bad. So what we want to do is to protect our entry points by data validation. One way to do that is to use a schema language called JSON schema. And in JSON schema, we describe the expected shape of our data as data. For example, this could be the schema for the book. So the book, the type of the book is an object. Object in JSON means a map. The required fields are title and publication year. Title should be a string, and publication year should be an integer that is between 1455 and 2022. Why 1455? Because it's the date of the first ever printed book, the Gutenberg Bible. And that's cool because JSON schema is used at runtime. So I can inspect the runtime value, which is not possible with static types. I cannot express a static type for an integer between a range of numbers. But in JSON schema, it's part of the language. And I need to use a library in order to convert this JSON to something, to a schema, and to use the schema to validate my data. In JavaScript, there is a library called 8JV for JSON schema validation. And here I will do something very, very simple. In my code, book info, before I execute the body of the function, I will validate that what I receive as an argument, the function receives as an argument, has the expected shape, is valid according to my schema. And if it's not the case, I will throw an error and with an explanation, a description about what part of the validation failed. So I will not fail silently. Instead, let me show you what happens if I'm parsing a valid JSON, but a JSON that does not describe a valid book, and I call book info with this invalid book. Now I will have an exception that says book info called with invalid args and with an explanation returned by the library automatically. Data should have required property title. And this could return back to the user as with probably a 400 bad request error. And anyway, we need to do so no matter if we use types or not types. We cannot use types in order to make sure that data over the wire is valid, or even if we do so, we will not detect it at compile time. Of course, the error will happen anyway, only at runtime. So in a sense, JSON schema is more powerful than types because we can express dynamic properties of our data, and also more flexible because we can decide where and when we want to validate. The flip side of it, the downside is that it's not mandatory. So sometimes we can forget to validate type and we will have very bad behavior of the system. As I mentioned, JSON schema libraries are available in probably virtually any language. In JavaScript, we have AGV. In Java, we have Snowy JSON. In C# we have JSON schema. In Python, we have GSCON. In Ruby, we have GSCON schema. And I'm sure that in Scala, there is something also, and probably in any programming language. So before we wrap up this presentation, let me tell you where does data-oriented programming come from? I did not invent it. In fact, it has its root in the origin of programming. And when John McCarthy invented Lisp in 1958, in fact, Lisp stands for list processing. And John McCarthy suggested to represent data using immutable lists, and he planted the root of the first data validation functions, and it was done in a generic and immutable way. Then in 1981, Bruce McLennan published a very, very nice paper, called Values and Objects in Programming Languages, where he clarifies the distinction between values and objects. Objects not in the sense of object-oriented programming, but in the sense of something that has a state, and values something that doesn't value as something that does not have a state. Then in 2000, Phil Bagwell invented a data structure called ideal hash trees. It was not related to data-oriented programming, but in 2007, Rich Hickey, the inventor of Clojure, used the ideal hash tree data structure in order to provide an efficient implementation of persistent data structures. But just a year before that, Ben Mosley and Peter Marks published a paper called Out of the Tar Pit, where they clarified the distinction between, so first of all, the definition of complexity that I mentioned at the beginning of my presentation as what makes a system hard to understand comes from them. And they suggest a distinction between accidental complexity and essential complexity. Essential complexity has to do with the problem that you try to solve. And if the problem you try to solve is hard, it will be hard to solve it, no matter what programming language you use. But according to the authors, many times, because we use the wrong technology, the wrong program or the programming language or the wrong paradigm, we add in top of this essential complexity a bunch of accidental complexity. And in fact, data-oriented programming is a way to reduce the accidental complexity of our system. And the core of it is the persistent data structures and the immutability of data. And since 2009, the persistent data structures implementation from Clojure has been ported to all programming languages. So today, in 2022, there is no excuse to mutate data, and it should be avoided by all means. Let's summarize. Data-oriented programming is about treating data as a first-class citizen, and for that, we need to comply with 4 principles. First of all, we separate between code and data. We can write our code either in FP style or OP style, doesn't matter. Then we separate between data representation and data schema. That's principle number 4. It's not in order. And for representing data, we prefer to choose generic data structures. And by no means we allow ourselves to mutate data. We leverage persistent data structures to manipulate data in an immutable way. Can we take questions on YouTube? Let me check.
Yes.
There were questions. Okay, just a moment. I'm trying to find my YouTube window. It was there, but...
Hello.
Hey,
Hey.
I see there are questions.
There is not a question, but or a question or a what do you call
Oh,
it?
that other way is a great book. Thank you. Performance issues is the biggest pain point while trying to inform my colleagues. Right, but if you use, so first of all, if you don't have huge data structures, you can use the structural sharing trick I mentioned, and it takes 7 lines of code to implement it. I can share the implementation. Can I share stuff on YouTube?
Sure.
On Zoom?
Let's see.
Okay, I wrote an article about that. 7 lines of code to implement structural sharing. Let me find it. Okay, structural sharing with 7 lines of code. All right, so that's naive structural sharing is a good fit for non-small to medium hash maps up to 1,000 entries at each level. And if you have more than that, then you need to use the persistent data structures library taken from Clojure and that have been ported to all programming languages. There is another little challenge, is that if you are used to write your code in such a way that it mutates in place, it would require a bit of effort to get used to not mutating in place. But there is no real performance issue unless you do something, I don't know, you write an operating system, or you need to launch rockets on the moon, or to do trading, or not data mining, Bitcoin mining or stuff like that. But if you do regular web development, backend, frontend, you should not have any problem with persistent data structure. Okay, exciting, getting this to other languages was one of the most exciting about learning Haskell. Yeah, I don't think it's part of Haskell, by the way. Haskell is popular for being immutable, but Haskell does not really provide the structural sharing trick I mentioned. They do something slightly different. All right.
All right. Thank you
So
very
if you
thank you
want to
very
go
much for your
deeper,
presentation.
you can take a look at the book. That's it, basically.
Thank you very much for your presentation. When did the book come out?
It came up, I think in the print version in July.
Oh, this year?
Yeah, but it was available for a long time as a MeetUp and ebook.
Oh, okay.
Now it's even available in audio.
Oh, okay. Thank you very much. I wrote an application in the end of 90s, a CMS for a web for web, and I should have read this book or heard your talk before I did that, because they more more or less ran into everything what you discussed here.
All right.
Yes. Yes. Again, thank you very much, and also thank you for all answering all the questions. Again, thank you very much. We'll put out links after we published like your presentation. We'll put out all the links and all to your books and everything. Again, thank you very much, Yehonathan.
My pleasure.
Yes.
Thank you.
With that, we'll go over to the next presentation and the next presenter. Welcome, John, and good morning.
Good morning.
Good morning. You're with us from the future, the 7th of December.
I am indeed. Yes, it's 5:45 a.m. Out here in very warm Brisbane. It's I think 27 degrees outside at 5:45 in the morning.
Oh my God. We have
It's going to get to,
-5 here.
oh wow, it's going to get to 34 apparently today. So it's going to be interesting.
Yes. So welcome to Func Prog Sweden, and thanks for waking up very early from the future. And let's head over your yes, let's head over to your presentation. This is not a Mona tutorial.
Yeah. So well, are we able to see the screen? Am I seeing the screen or not? There we go. Learning anything new, because anyone I spoke to is effectively used terminology and mathematics and different concepts, and every discussion I had basically made me feel like a complete novice. And I'd had 2.5 decades of experience at that time, and I was still not prepared for FP in some sense. So I soldiered on and basically worked in the FE industry for a while. I got the opportunity to basically write a new programming language for quantum computing using functional concepts, basically defining everything in terms of a free monad written in F#. And if those words mean nothing to you, that's perfectly fine. All I'm saying is that I've come a fair way. And the biggest learning I've had has been in terms of how to communicate these concepts to other programmers, some of whom may actually not have the foundation or, like myself, not have a clear understanding of some concepts. But mostly, I think we get it wrong when we talk about how we do this, because we usually bombard them with a whole bunch of new terminology and so on, which really is, I think, a non-productive way of going about it. So I'm going to try and take an approach with a common problem today and try and see if we can work out, what a reasonable solution might be. And then eventually we'll discuss how FP fits into it. And maybe that may be an interesting introduction to some of the advanced concepts to people who aren't necessarily interested in learning all the FP rigor to start with. All right. So I'll introduce myself. My name is John Azariah. I'm a principal engineer at Microsoft. I work on AKS. I have a functional programmer. I'm a functional programmer with a fair bit of experience in programming language design, and I am interested in type systems. And I've been doing this for some time. You can hit me up on email or on Twitter for as long as the website exists. At those handles. We'll come back to this in a bit. Right. So one of the more interesting or less interesting things that I do in my day job is to write Go code, right? And we've all written code like this. Turns out that in Go code, this is like the pattern that you follow. You call a function, check its error value, and then call the next function with values only if the error is not null. And you intersperse this error code all over the place. Perversely, this is touted as an example of how Go is easy to program in. I look at it from a type systems perspective and kind of laugh because this is exactly the wrong type to use. They're using a tuple to return a value in which both the components of the tuple may be set, but we only check for the error first by convention. What we really need is a choice type in this case, where you either get an error or you get the value. But obviously, this is advanced type theory as far as Go is concerned, and we're all told that this is the best way to do programming, and I actually don't think so. Let's go back and see what the problem with this code is. So first of all, you can see that, today somebody has actually gone through a recent code review and so on, and actually made sure that the error checks are there for every function. And you can check every time before you return. But you can quite easily see that this is a convention, not anything else. If sometime in the future, someone may decide to actually not do the error check and slide it past code review, and now you have a runtime configuration issue. So that's a problem. So we want the error check to basically somehow be mandated in this mixture. The other thing is it's really difficult to figure out what the heck is actually going on, right? What we really want is a condensed version of this code which doesn't have all of this noise. You want a signal to noise ratio that's better than what you have here. It turns out there's only 6 lines of code in this function and 12 or 18 lines of extra white space to do this error thing. And then let's meditate on this for a bit, right? Like part of the problem is when a function, say like the very first function here that says config returns a JB config. Once config returns the JB config an error, it doesn't have any control at all about how to mandate the error check. There's no way for config to control how the caller is actually going to use the return value. Right? There's no way to do that. And in some sense, that's what we're asking for, because we're really saying that in order for us to basically write these things out in a nice, safe way, the calling function needs to somehow have the ability to tell the caller, look, behave this way, otherwise, you're not going to be a good citizen, right? And that's a problem. That's the problem we kind of want to solve. So 2 problems. One is we want to make it so that the code is less noisy. The second one is we want to make the error checks mandatory, right? So this is what we just said. So what we need to do to wrest the control back is to basically say, okay, look, let's use, first of all, let's use the correct type. Let's make it a choice type. Let's make it so that you can either have a value or an error, but not both, right? And then, so that let's make that happen. And then make sure that the caller has no choice but complying, right? The caller has to comply with the rules, because the called function is going to return the value in such a way that the caller really can't make a choice. Now, the F# people here will look at the succinct choice type over there, and then they would look at it and say, look, we are going to basically just do error checking like we used to, the same way as Go, right? Pattern match and so on. But we don't want to do that. Let's just step back from that approach and just look at it as error check is this code. Now it's a class that basically wraps a value or an error and doesn't let you decide which one it is, and doesn't let you actually get a handle to the value, right? So in some sense, when we do that, we have this kind of code that isn't quite working. Like there's no real way to make this work just yet. But ideally, we've encapsulated the error piece into this error check thing, so we can comment out those error checks, and we'll end up getting a lot less noise in the code if you ignore the comments. Right? So let's take a look at what we've done. We've made it so that the caller can't cheat the error checker, and we've removed a fair bit of clutter, but obviously we've left the code completely broken. Nothing's actually happening at this point. We can't even call the next function because the next function doesn't know what to do with this wrapped type. So let's move on and see what we can do next. So next thing we can do, because we're kind of functional programmers, we kind of know the answer is instead of asking the caller of this function to unwrap the value, which is what was happening in the Go code. If you remember, we were trying to figure out whether we had an error or whether we had a value. We unwrapped the result that came back from the called function, right? And then using the called value, instead of doing that, let's actually make that call a responsibility of this wrapping class. So we'll add a method on the wrapping class, which is literally the only way you can get a handle to the internal values. Except that we are going to be super smart, and what we're going to do is we're going to pass in a lambda. So we're not going to give back the value to the caller, right? What we're going to do is we're going to say, I have the value, you tell me what you want done with it, I'll do it for you. And we implement that code. It's actually a very simple piece of code. And in fact, when you do that, it means that this pattern matching thing happens in this helper class. Helper method. You don't have to actually write the wrapper class. You don't have to write the match function everywhere. And that might actually reduce your signal, increase your signal to noise ratio, reduce the clutter in there. And if you do that, then we can force the error checking to get done every time we want to get started, right? So the code looks something like this. Now, when we want to do that, we have to chain the calls somehow. We have code now that doesn't quite work because we only know how to pass a lambda in, but what lambda are you going to pass in this case? So let's take a look at this code here. What's actually going on? Well, we are returning a JB config. Let's ignore the error for a while. Let's say that the internal check is going to take care of it. And it's going to return this config thing into some blind piece of code, which doesn't quite work, right? And you need to pass that into the second line argument. Now, what I've done is I've taken the Go code, which works, and made a kind of pseudo C#-ish code just to simplify it. But this is really all that function is doing, right? And if you take, what we want to do is the value of config, the first line, the value of that function comes back as an opaque object. Now, you don't have access to the object. All you have is this lambda. And now you say, okay, how do I pass how do I pass in a lambda in here that uses the unwrapped JB config internally, right? And the way to do that is to basically turn the rest of the function, starting from the second line onwards, into a lambda, right? And then call that with a given argument. So effectively what happens is you take this config thing, which returns this wrapped value. The wrapped value has a method called call with value on it. And call with value takes a lambda, which then takes the unwrapped value as part of the argument and passes it to the rest of the lambda. Now, of course, if we do this for the entire function, you'll end up with something horrible, right? You'll end up with this huge chain of functions, each of which effectively executes one line, gets some wrapped value back from that one line, and then calls the next line as a lambda so that it unwraps the value and passes that on to the next piece. Now, this is kind of interesting because what we've done here actually has we've basically turned the problem inside out, and we've turned this piece of code very mechanically into that piece of code, right? And it's really a mechanical translation, but we've taken care of enforcing the error check in there, and we've ensured that the composition of these functions works. Now, if you look at this a little carefully, you'll realize that they're all in tail call position, as in this function, call with value, never returns, is the only thing that returns in this entire function. Everything inside it also takes its entire block and returns just that one value. And because of that, we can convert this whole thing into something that uses constant stack space. Now, that doesn't mean much. All it says is we haven't made it worse, because this piece of code also used constant stack space, and this representation also uses the same constant stack space. We haven't made anything worse. All we've done is turned the inversion of control inside out and found a way to pass the internal values to the rest of the function. And therefore, these two pieces of code are actually equivalent. So having done that, what's our scorecard? Well, we've done the error checking. We've removed some clutter. We've passed values on to the next function and so on and so forth. But God, the code is ugly. I mean, seriously, we can't expect somebody to read that call chain and expect that to be reasonable, right? And now this is where it starts getting a little interesting. While we're technically successful, we're not at a point where it's actually useful. So what we need to do is provide some syntactic sugar to this. So let's take a look at this lambda. What this is basically saying is there's a call with value that passes on the next bit to it. What we really want to do is somehow capture this value, jbconfig, and make that available in some context to the rest of this function. Now, this is kind of what we implicitly did in the old days with the semicolons, right? Like we had a semicolon that said jbconfig equals config, and then a semicolon, and then that passed the jbconfig forward. What we're trying to do is now add this context where it's not just blindly call the next function, but also do this call with value piece in the middle. So let's look at this thing, and let's look at how we do it in F#. Now, one interesting thing to realize is that we can always get to this representation with any language that allows us to represent lambdas. But to go from here to the syntactic sugar piece, even if all the languages that we know of are going to be Turing compatible, there's an enormous difference between which language you pick, because the support for allowing you to put syntactic sugar on top of this representation is very much a function of the language. So in F#, that syntactic sugar is called a computation expression. You do that by adding these two methods called bind and return. They're well-known functions. You don't need to add them into the class itself, but you need to add them in this error checked builder class, and you create an instance of this. And when you do that, then you can write a bit of code that looks very similar to the standard F# code, with the exception of this let bang thing and this error checked context. So what this tells you is that in this context, please use the error checked wrapper and call through its call by value between every single invocation in here. And inside that context, you can unwrap the value. So this let bang basically allows you to unwrap the value of what config would have returned, which would have been the opaque value. We unwrap it, take its value out, call it jbconfig, and make it available to the rest of the sequence of instructions, right? And this is just a syntactic sugar transformation. This is syntactical sugar that does this. So we've converted that horrible looking chain into this by just using this feature of the language. Well, what about C#? C# doesn't have computation expressions, but it has another way of actually providing syntactic sugar for those kinds of call chains, and that's called link. So link is a little bit more complicated because that call by value actually meant two different things. Either you could call an operation that returned an unwrapped value or an operation that returned a wrapped value, and the operation of those is actually slightly different, right? So if we enhance our error checked class to do this, you still have no way. First of all, you have only one, you have ways of unambiguously creating either a value or an error, but not both. And there's no way of actually pulling the value out and checking, hey, are you an error or are you a value? So the caller can't do anything with this value except call map or bind on it by passing in an appropriate lambda. And due to the brilliance of people like Eric Meyer and people who built Link, all you have to do to basically provide some syntactic sugar is to implement this select many method on it. And this extension basically allows us to export the capability of this class into C#. And literally what you need to do for any other context that you want to write is change this link, add another extension method for this link method. That's it, right? And when you do that, you come up with this syntax, which actually works. The only thing ugly about it is that there's no tuple destructuring in link, which seems to be a kind of an odd exception that they have at this point. But fundamentally, you could quite cleanly write out the code that represents these sequence of instructions in the context of doing error checking. And C# allows you to do that. So we have a nice, easy way of doing this. So I'm going to make the claim that in both C# and F#, we have met the goal that we wanted to achieve, which is we want to make sure that there's no way to bypass the error checking by either malice or neglect. There's no way to actually you introduce clutter into this, right? The clutter of doing the error checking is completely abstracted and hidden away. We ensure that it's done. We ensure that you can chain the value on to the next function. And the argument is that this code is actually not horrible to read. It's actually quite easy to read. It's a little bit non-typical in terms of it's slightly different from your semicolon separated C#, but it's still clean and it's still unambiguous and scopes work and so on and so forth. Right. So what have we actually done? And this is the piece where I want to actually focus a little bit of time on. I mean, we've kind of like rushed through the mechanism of the mechanics of what we wanted to do, and we've done some refactoring, right? So where does FP fit into all of this stuff? So let's summarize what we want to do in the first place, right? We wanted to basically say, We want to consistently error check the result of functions, and we don't want the error checking to compete for attention. Right? That's naively what we wanted to actually do. But after like a little bit of thought, a little bit of analysis, a slightly more insightful approach is to actually state the problem this way, which is we have a boilerplate pattern. We want to take that out from the code, and we want to push the boilerplate into some context so that a sequence of code can execute in that context, and boilerplate is taken care of. That's really kind of what we wanted to do, and so we went ahead with this approach. Now, there are many approaches that we might have been able to take, right? So I'm not going to say that this is the only approach we could have taken, but as it turns out, it seems like a very good approach for many reasons, and we can discuss those later, right? Let's talk about what we did was. What we did was we wrapped all the return values so that we didn't allow the caller to take access to the internal value. And because we didn't allow the access to the internal value, the caller doesn't have any idea of what to do with this context wrapped object, except to invert control and pass a lambda into the context to say, hey, run the rest of this code, run this lambda in the context that you have. Now, the lambda itself doesn't know that it's running in any specific context. And that's a very profound observation, because actually it means that you can change context, so you can increase you can enhance the context, so you can even completely replace the context and keep the sequence of the code that you want to execute exactly the same. And the code that you're trying to run will run in the new context. So say, for example, we wanted to add logging to each line of code. Now, you would say, okay, I would have to stand in there and write all the lines of code for logging and so on and so forth. But if we push that into the context, into the boilerplate, the lambda actually doesn't have a clue that it's actually doing anything. The wrapper, on the other hand, knows that a lambda is about to be run. It knows that an argument is coming in. It knows that it's going to be called. So it can log the value. And you can actually introduce one line of code in the boilerplate and push that context, enrich the context all the way for the entire sequence of things. The other reason why this is profound is actually because it doesn't matter what the context is. If you have no context at all, that's like a normal sequence of instructions. It's just like a standard sequence of instructions, just separated by semicolons. And that's no context being passed around, or a specific kind of global context being passed around, which effectively means that even the semicolon-based representation of a code is actually a chain of continuations. You can look at it the same way, and we'll come to that in a minute, because that's really where the whole FP perspective changes. Anyway, once you perform the inversion of control, you convert your instruction sequence into this chain of continuations, and then you can apply syntactic sugar to flatten that continuation chain into some palatable syntax. Of course, you can only do that if your language allows you to do it, which is why different programmers with different language proficiencies look at the same problem differently. And that's really a very important observation, because if you start with the context of knowing one language, and you view code in a particular way, that somewhat impacts how you view the kind of thing that we're doing right now. So for example, with Haskell and Scala, all of these continuation chains, independent of the context, have the same syntactic sugar capability. You can basically lift the context of any continuation chain and make it look the same with Haskell and Scala. And so Haskell and Scala people will look at this talk and say, what a boring talk. He hasn't done anything interesting. He hasn't talked about any of the hardcore mathematical concepts behind any of this stuff, or even talked about why this works, and he hasn't used the C word yet, and so on. This is bread and butter. This is our normal way of looking at it. What's the big deal, right? F# has different syntax wrapper for each context, but the syntax inside the wrapper is going to be universally the same. So you always use let bang when you want to unwrap a contextual value. You always use return when you want to take an unwrapped value and put it inside a context and send it out, right? And it becomes part of the idiomatic usage of the language, and all F# programmers, after a small bit of familiarity with the language, will know how to use a computation expression like sequence or async or whatever it is. And its uniform syntax for each context is just that the name of the wrapper around the context that changes. So they're looking a little bit smugly at this, saying, hey, this is like how we do our stuff. We're actually, there's no difference between seek and async. All you have to do is change that, and then your let bangs just work, and so on and so forth. And their approach for looking at this is, again, going to be from that viewpoint. C# people will fall in two broad categories. There'll be a small group that's familiar with LINQ, and they'll be familiar with how to use it. Like, okay, I see. So if I use the contextual extension method, then I can just use LINQ syntax, and that does all of the unwrapping and the wrapping and the injecting of the syntax or injecting of the boilerplate into the code and so on, and everything is fine and dandy. But the vast majority, I would wager, given the experience that I have of working with C# programmers, they would look at LINQ and say, look, that's sort of hurts my head. I don't need any of this. It's kind of like a scientific curiosity, Yeah, some people might need it, but really it's not very, very useful for my everyday life. And that is really the tipping point, in my opinion. Like, they have the ability to realize that something can be done, maybe don't necessarily use it. C# also makes it more difficult because for different contexts, certain well-known contexts, they have different syntax completely for this desugaring. So, for example, you have the Elvis operators and to the next function if the value is not null. They also have a completely different, completely inconsistent syntax for async. So we write async and then await, and what await does, it exactly does the same thing. Await does the unwrap of a function that is run inside the context of an asynchronous thing. And so people who look at LINQ, double question marks, or the Elvis operator, and async, begin to think of them as three different types of things. And that is the perspective with which the language has kind of led them into that point of view. And you can't really blame them, or it's not a reflection on anything other than their background that allows them to look at that perspective. And so informing them about how any of this stuff matters or why is all of this interesting involves looking at it from their perspective and then coming at the problem from there. So in some sense, that's kind of what we did today. We took a fairly common problem. It's pervasive all over the place. Oh, and by the way, Go has no way to apply syntactic sugar. So the only thing you can do is do the call, the continuation chain, which obviously is not palatable. And now a Go programmer will look at this and say, why the hell would I want to do that? The best way you can always do stuff is to put the if error equal not equals null check everywhere. That's the best way to do it. That's the best way to do error checking all over the place. And again, you can't really blame them for having that perspective because their language doesn't allow them to give that syntactic sugar in there. And so the idea that having syntactic sugar allows you to do something much more powerful doesn't have any relevance at all to their point of view. So they looked at this spectrum. It's called the blob paradox in a paper that was written a long time ago. If you look up the spectrum and you say, why the hell would I need that feature? I can do everything I need from here on down. That's not a function of their intelligence or their capability or anything of the sort. It's just a function of the context that they have and the familiarity they have with the language, the affordance of the language that they have, which allows them to basically not necessarily see the benefit of something that is more abstract. And that's really what the conversation is we're looking at this blob paradox. Everyone's comfortable where they are. Everyone has a perspective of why something matters and how I can do something. And it's a hard slog to pull someone one level up because fundamentally there is no perceptive need for that. Go programmers are happy to sit and write if not equal nil every day of their lives, morning to night. Trying to tell them that you can make your code a lot less cluttered and force you to always do the if check automatically has limited value because they cannot see that within the construct of where they are. But with some other languages, it's worth the slog to go back up. Now, the key perspective from an FP perspective is that all these three blocks are actually the same thing. They're actually the same thing. It's a completely mechanical process to go from the first block of code into the second representation. Because really what you're doing is you are saying, hey, config will return some value. In the null context, call with value simply calls the lambda that you pass with no value at all. And that's really what that semicolon really looks like. If you remove the semicolon and replace it with call with value, and you take the argument and pass it down, you'll get exactly this. And in the null context, call with value simply just takes the value and passes it on to the lambda. So there's a completely mechanical way of going from here to here. And there is a completely mechanical way of going from here to here using whatever sugaring construct is available. Now, if call with value was just the identity, as in just pass the value along, then this extension method, once you write it for that null context, this code and this code would do exactly the same thing. But if you enrich call with value to do something else, then all of a sudden, this code will have exactly the same structure as this code, but with all of the boilerplate that you want to get executed, injected and streamlined into the process of this. And when you look at it from an FP perspective, what have we actually done here? We have talked about representing code as a lambda. That's the functional piece. And then composing these lambdas together in the context of a concept, I mean, within a context. So you composed, and this is the first time using that word, you've turned this problem into a composition problem where the composition is composing in the context. In this particular case, the context is the error-checked context, which does an error check for every single value. And you've turned that composition into a nicely sugared format. And it turns out that this context is effectively just composition. This is all we're doing is this composition. It's composition within context. We spent a fair bit of time to get here, but that's all we've done is just do composition, function composition within a context. And that's why this isn't a monad tutorial. Thank you.
Thank you very much, Jon. Very, very, very interesting presentation. Thank you very much. Yes, let's see. Let's head over to see if there's no questions so far. How come you got into this kind of functional programming?
So I got into I was a C# programmer from the time C#, well, actually from before C# became C#. I was programming in .NET. I was part of Microsoft in the days before .NET, and I was one of the people that worked on a little-known language called J#, which was effectively Java on the .NET CLR. It was an abandoned project after we shipped version 1, but that was one of the first. So I was basically working on .NET for a long time. I learned a little bit of FP in college, but obviously, there was no real functional use of it in industry until much later when JavaScript came out and we started writing web applications. And I was introduced to 2 or 3 seminal papers on using continuations and that kind of thing in JavaScript. And then from there on, I had an interest in programming language design and code generation. So functional programming became very much a foundation of that, because you're transforming code, and when you do that, you're really transforming functions. So you're trying to find ways to actually represent functions and then transform them and so on and so forth. And eventually I landed up getting the opportunity to work in Scala. And I got a deep dive into the whole applicators and functors and monads and all of the other stuff that the big terminology and everything. And it was a fascinating time because for a year I was probably one of the oldest people on the team, but one of the most junior in terms of understanding any of these concepts. And I kept learning a lot of stuff, which turned out to be very useful. So when I landed up working in Microsoft and getting involved in the quantum programming team, we landed up having to find ways to encode instructions to go down to the quantum computer. And I looked at it and I'm like, hey, that looks like a language to me, And so we eventually implemented a pseudocode of that language using a free monad, and we had to write the free monad interpreter, and because there could be tens of thousands of instructions, you run out of stack space. So we landed up implementing a trampoline, and all of these heavy lifting pieces came from the FP experience that I had. But in the process of doing all the heavy lifting, I was working with a whole bunch of really smart people who had no idea what the hell I was talking about when I used any of the terms. And so the joke is that every time you have a conversation with John, you'll bring monads into the conversation. And what the hell is a monad? And so I tried many times to have a gentle introduction to monads, failed miserably. I think at the end of it, coming at the problem from the perspective of somebody who has coding problem they can relate to, and then introducing them to the pattern without necessarily bringing in the category theory, I'm hoping that actually works out as a better, gentler introduction to the concept, and that should trigger some aha moments like, hey, those three things are actually the same thing. Or, hey, what if I have a different context? Or, are there any other patterns that look like this? Now, this pattern is about composition and context. What are the other patterns out there? And those are questions that come out of curiosity. And then we can talk about the terminology, and then we can introduce them to the foundations of why this stuff works. Why is it rigorous? Why is it better than anything else out there? And that conversation comes later, not at the beginning, which I think is the mistake that we all make. There is a famous blog post out there called, don't write another monad tutorial or something, which effectively talks about exactly the same thing. Somebody who's understood monads has this aha moment and wants to communicate everything at the same time to somebody who has not come across on that journey yet. So there's a whole bunch of implicit knowledge that you have accumulated for the bit to flip at some point. And you're talking to an audience that may not have had that flipped bit because they can't relate to the problem you're trying to solve. And I'm hoping that this talk actually moves in that direction.
Yes, it certainly did. Thank you very much again, John. Thank you.
Thank you. Take care.
Thank you. And with that, folks, we are done for tonight for the last Func Prog Sweden this year. Then we will be back again in January. We will hopefully be able to live stream also from Vietnam and Ho Chi Minh City. And then we're back here in Sweden on the 17th of January. And then we'll do one meetup per month in next year, as we've done this year. So with that, have a nice December, a Merry Christmas, Happy New Year, and see you next year. Bye.